Workshop on hydrogen production, technologies, and energy uses. This is a program for 3 days on awareness creation and capacity building among students and teachers. Uh, I am going to talk about the workshop theme. We are holding this program with Climate Change Research Institute, and yesterday I think you had a very exhaustive session talking about how the hydrogen can be produced and the various latest research, what is hydrogen economy, how it works. Hydrogen economy is basically shift, because once you have hydrogen as a main fuel, then right now we have coal-based economy because we are coal-dominated country. And if we change the fuel from coal to hydrogen, then we say it is hydrogen economy because we think of producing hydrogen, we need this infrastructure for hydrogen and its use in various sectors. So once it starts having the major share, I mean, at least significant share, then we say we are moving towards hydrogen economy right now, trying to build up a case. So uh, yesterday, I think there was a lecture on okay. Okay, so what was okay. Green hydrogen production, hybrid approach. This is the technical session today. Uh, First of all, the climate change context. We are doing it essentially from the viewpoint of climate change. Because as you may recall, yesterday, Professor Yadav said that it was going very slowly initially, but now it is going in a very fast mode. So because earlier it was thought as an option for clean energy only, pollution, reduction of pollution, but now it is also considered important for reduction of greenhouse gas emissions. And so it is a climate change context which has made it rather more significant, and accelerated action have been targeted worldwide. The sixth report of the Intergovernmental Panel on Climate Change was released in the August month. The one part of the report, which is released in April, stated that if world is to reach net zero emissions, hydrogen will play a very vital role. So they were advocating both for hydrogen and carbon capture and storage from the coal sector. And yesterday also there was a talk by Dr. Miss Gauri Johar, who talked about the role of CCS in transition. So the key challenges for hydrogen are cost-effective, low zero carbon production, delivery infrastructure cost, land area requirement of hydrogen pipelines, compressor stations, other infrastructure. So these are the things which need to be addressed, not only one production or use, but I'm just telling the challenges in using the existing pipeline infrastructure. Because, for example, EU has said that they can use the natural gas pipeline for hydrogen transport, maintaining hydrogen purity, minimizing hydrogen leakage, and the cost and performance of end uses. So these are the number of challenges which have been identified from the Intergovernmental Panel report. So this is a diagram which is showing annual carbon dioxide emissions by region wise, and it says that over past 8 million years, the concentration of CO2 in the atmosphere was fluctuating between 200 to 300 part per million of molecules. Now, since 1950, the atmospheric CO2 concentration have grown from about 310 to 421 in 2021, which is almost equivalent to the value at 4 million years back. So if it is going that fast, we are already approached 4 million scenario, then 8 million scenarios. No, I mean, the disaster or catastrophe is very near, which will affect the whole planet Earth. And these are some of the pictures. We have the pointer in this. Which one? This one?
Difficult to make point.
Okay. It works.
The one on top
Hmm?
there. This one.
Acha, this one.
Yeah.
Okay. So on right hand side, you can see the major emitters: China, India, US, and EU, which added to up to 70% of the total increase in CO2 in last 50 years. And then this is just a diagram to show how the annual changes in these countries are taking place. And the black line represents the total global annual CO2 emissions from the world, from these countries. Sorry. Okay, this is again on climate change, and we are trying to indicate to you that sectors of economy which are being affected by the greenhouse gas, the contribution they are making to greenhouse gas emissions. Like normally we talk that energy sector is the highest, but these are all the sectors of economy where electricity, industry, building sector, and all other sectors, transportation, they all contribute to greenhouse gas emissions, and the proportion in different proportions. And if you see the diagram below, one, it shows the emissions from electricity sector. It is the maximum energy sector. Then from various other sectors, it is showing that this one is the industry share. So you can see that this is the highest share of the global greenhouse gas emissions. And on right hand side is the forecasted hydrogen production volume by region, which is expected to be there in 2025, which is that Asia Pacific will have a 45% share, whereas America, Europe, Middle East, and Central South America, their share is also indicated. So which means that Asia Pacific sector is going fast to produce hydrogen in their kitty. Okay. This one is showing the hydrogen production pathways from our existing current energy systems. We all know, we discussed also like offshore wind, onshore wind, wind machines, solar PV, solar photovoltaic, then this dam reservoir plants. We were talking of the pump storage, PHS, then run of the river plants, small micro hydel projects, and coming back to this biomass and the fossil fuel. All are the sources of energy in different proportions. We all agree that whatever electricity or energy we consume, we are using all these sources, and these are all can be connected to hydrogen. This is a diagram adopted from an existing diagram. What we are trying to show is that if you have, say, from offshore wind, that energy can be used for producing hydrogen. Similarly, all these energy finally can be used for producing hydrogen, and even the nuclear energy here can also be used to produce hydrogen. So hydrogen then can be stored and meet the demand of industry and electricity sector. So this is how the current, this depiction I liked, so I thought I will adopt it to simplify. And so now I come to the hydrogen production technologies. Now production technologies are so many. I think maybe more than two dozen, but they can be grouped into four categories broadly, which are electrical methods, thermal methods, hybrid methods, and biological processes. So they are grouped into four categories, and we'll briefly discuss each one by one. Okay, electrical methods are mainly electrolysis. Electrolysis of water, we know, can produce uh, hydrogen and O2, oxygen, separate H2O molecules can be used. Sorry. Okay. So, water can be electrolyzed by passing electrical current. That is mainly the electrolysis. There is a cathode and there is an anode, and but the conditions for the water splitting require energy. This was even developed quite early and was known as redox reaction, but it was needing so much of energy that it was not very much popular. But now, when we are talking of green hydrogen, we are saying this is the only way. This may not be the only way, but this is the focus. So this is showing the simple water electrolysis by water splitting by electrolysis, and on the right hand side, you can see here the plasma arc electrolysis. Now, plasma arc electrolysis is basically raising the temperature. If you can raise the temperature somehow by plasma techniques, you can, this is the water, and water can be again dissociated into its molecules. So this was also talked about yesterday as a thermomechanical experiment, thermomechanical conversion. So some of catalysts are used in this process, but this is basically the electrical process. Now, the thermal process is basically used for the fossil fuels. That means increasing the temperature. So if we using coal, then we are gasifying the coal, or we can use natural gas as of it, or we can use petroleum refinery products. So this diagram is suggesting you how the hydrogen by gasification, and then the components can be separated and hydrogen can be produced. The main reactions, and below diagram is showing you the current methods being used, like methane steam reforming. Those who are dealing with the coal technologies for electricity generation, they are very familiar with this steam reforming and the oil reforming, or oil refining, products conversion, coal gasification. I mean, these are all terms which are used, but then there are so many challenges in each of them, and then they need to be coal gasification. I mean, the gas obtained from the hydrogen obtained from these methods require further removal of carbon dioxide, because the carbon dioxide emissions are higher. So that's why the colors of hydrogen has been assigned. A colorless gas, odorless gas, which does not exist in very scarcely exist on the free form on the earth, but it has many colors. I'll show you, and we'll discuss. And on the right hand side is the picture for India, which is saying where the refinery industries exist and we can have the potential of hydrogen production. So the production potential is high. Now, how much we can achieve is a matter of discussion. Okay. Then the biological process. Biological process basically are biohydrogen production methods by fermentation and photosynthesis. We are all familiar with that. I think Mr. Vashni is also going to talk about this quite in his lecture tomorrow. So there are further groupings like photofermentation, dark fermentation, direct biophotolysis, indirect biophotolysis. I'll not go too much in detail. Just giving you glimpses of what techniques are possible. Okay. So let us see what is biophotolysis. Photolysis is actually a process of electrolysis where in presence of sunlight, if we use some catalyst, then we can perhaps accelerate the reaction to separate the electrolysis. And we did not go to that high temperatures or energy supply. So that helps. By use of catalyst helps. So photolysis is adopted because some of the metals, iron, and their combinations are found very useful for obtaining electrolysis. But when the matter is like microalgae, microorganism, then it is biophotolysis. So microorganism can also be converted, and in that case, the hydronase or nitronase, you can see, genes, they are used as catalyst. These is the catalyst here, or it can be this one is catalyst. So this is a direct for biophotolysis, and this is indirect biophotolysis, and they are actually the enzyme or catalyst which help in reaction to produce hydrogen, and they are much cost effective. So these direct and indirect methods come basically as a hybrid processes. Then photoelectrochemical cells, they are also hybrid processes for production of hydrogen. And photoelectrolysis is a very innovative technique because it uses the semiconductors, very thin the slice of semiconductor resembles artificial leaf. And these semiconductors are actually, they can be either P-type or N-type photo sensitive on cathode or in anode, but they can produce hydrogen in, if that process is successful, it is considered the most cost-effective and innovative process. So that means we can create a leaf which goes photosynthesis to produce use the chlorophyll as catalyst and produces the growth of the plant for the use. And we can use the same process using semiconductor thin wafers and obtain the hydrogen. So this is a latest development which is now getting into, many groups are now working worldwide, especially in USA, also in India. So this process is a combination of photo-electrochemical process. Then there was a thermochemical process. There is also microwave use for hydrogen separation. There are so many hybrid approaches are there. So we can go on to that. But let me now come to the one of the output of this this artificial leaf, which we can have prepare our own, for hydrogen production. This is an achievement of National Chemical Laboratory Pune, which has developed ultra thin artificial leaf device consisting of semiconductors stacked in such a manner to stimulate natural leaf system, which I was explaining. In the presence of solar light, electrical current flows through the semiconductor and results in the vapor splitting the water splitting for hydrogen and oxygen. And they are so much promising that if we can have an array of solar collectors falling on this semiconductor system, which can be very small, maybe 2 inch by 2 inch, and then we can have an array, then we can produce solar factories and get hydrogen in bulk. So it is a promising method. So this is one achievement. And this next, what I want to really highlight is that if we look into the number of technologies for hydrogen production, probably we can identify some of the green hydrogen technologies that other than electrolysis. And those green can be water electrolysis using electrical method is, of course, we know that if we have the water is splitting by energy other than, not the conventional electricity, but solar, then it is green hydrogen. So this is one. Then biomass gasification is another CO2 method. So it is also producing green hydrogen. Then photoelectrochemical, I just explained to you, is producing green hydrogen, and photo fermentation also can make produce green hydrogen. And biophotolysis also we discussed, which is a biological method making hydrogen green. So green hydrogen can be produced in several ways, not only by just simply electrolysis of water using sun and solar energy. What is being suggested that to this thing, that solar energy is intermittent, and solar energy, if you want to use, we need a storage. So if we can use solar energy in combination for hydrogen production, we can have a continuous process. So that is the basic advantage of using. So this is one of the study which has identified a number of technologies have been studied and come out with this conclusion. So these are the possible green hydrogen pathways we are suggesting to be studied further. And then I talked about the color of hydrogen also, and everybody yesterday also you heard color of hydrogen. So it has so many colors, not colorless. So one of the coal is carbon and hydrogen with higher ratio of carbon to hydrogen. Actually, carbon and hydrogen are two elements which are part of all living, non-living systems on Earth. So if we take coal as a base, then if we can separate hydrogen from coal, it will be brown hydrogen actually. This is given the brown color. And white hydrogen is a byproduct of industrial processes. Many of the industrial effluents, they produce hydrogen, and if that is taken, it is given as a white hydrogen. Then we have gray hydrogen, which is produced from the natural gas. Natural gas hydrogen is gray hydrogen because it also produces some carbon dioxide, and coal produces more carbon dioxide, coal gasification, if you gasify the coal. So finally, the purple hydrogen through electrolysis using nuclear power. This is a pink, actually, pink color. So if you use nuclear energy, it is called pink hydrogen. And if you use electricity directly from electricity, conventional electricity, it is yellow hydrogen for water. Water, if you use solar energy, it is green. If you use electricity, it is yellow. If nuclear energy we use, it is pink. And then blue hydrogen is one which is produced from the gas. And from the gas, it is CO2 is separated. So we have to have both carbon capture and we have to have separation. And then there is a turquoise and then green hydrogen I have already explained. So I'm coming to the uses. The consumption, global consumption is suggested to be more for ammonia production also, and petroleum refinery industry, methanol. So these are the various ratios for highest is for ammonia production, petroleum is 25%, and methanol production is this is a global scenario. So users of hydrogen in various sectors. And if you look for the how the growth has taken place from 75 onwards, it is you can see that it was more for it was sorry. Yeah. So you can see initially it was more for the refining, but it has grown equally to the ammonia production. Refining products increasing. Okay, the next is how the DOE project. This yesterday also you must have seen. It is showing the various. This is a H2 scale is a DOE project, and I'll go quickly now. This slides are a bit troublesome now. various hydrogen uses are protected. This is for scaling up hydrogen production. It is a Department of Energy USA project, which aims for a larger production of hydrogen. So this I'll think I skip because yesterday also it was shown. And now I come to early initiatives, hydrogen initiatives in India. And way back in as early as 2003, India has given constituted a national hydrogen energy board. And in 2006, Ministry of Renewable Energy has laid out a national hydrogen policy roadmap depicting, identifying the transport sector and power sector as the major users and called it green energy at that time as a green energy initiative for the country. Then MNRE R&D program on hydrogen energy and fuel was also launched at the same time, and it will also develop the safe and efficient utilization for as fuel cells and for transport applications. Combustion R&D was intensified, focusing on improving the efficiency of the process, finding new materials which can be used as catalyst, because the catalyst cost determines the final cost. If you can use low cost catalyst, you can produce hydrogen at a cost effective manner. And more than 100 research groups engaged in fuel cell technology. And Institute of Chemical Technology, from where Professor Yadav came, and ONGC Energy Center collaborated to develop a cost effective production of hydrogen. So was telling yesterday that he has developed a plasma arc system, thermomechanical system, which is very cost effective for hydrogen production for electricity, which is would like it may cost, we were discussing, now it is $5 to $7 per kg, and it may come down to one. So he was saying it is less than even one. The other recently, there are more initiatives. I talked about 2006 scenario. Now, recent is that India participated in the Mission Innovation Challenge in 2015, along with the Paris Agreement, which also had clean hydrogen share objective to accelerate the development of global hydrogen market for various application and storage, etc. And India country's status report on hydrogen and fuel cell has been prepared by the Department of Science and Technology. If you write this name, you can find it on the internet. In 2020, Indian Institute of Science and R&D Center of Indian Oil Corporation have gone into an MOU to develop biomass gasification-based hydrogen generation. And 2022, Ministry of Power has recently announced a green hydrogen policy, making India as a green hydrogen hub. Okay, there are about 34 green hydrogen hub in the across the world. So India could become 35th or so. India's success stories: first electrical fuel vehicle based on hydrogen pilot was, he also mentioned yesterday, has been launched very recently by Minister Gadkari ji about the use by Toyota Kirloskar and ICAT in March. Then ICV are running hydrogen as fuel. ICV means internal combustion engines are also running on hydrogen fuel in place of CNG. CNG is used as a fuel. So they are tested in Delhi and Ladakh region with NTPC taking the lead. Am I right?
Yeah.
Okay. MOPNG has launched a hydrogen corpus fund for funding R&D and is planning to pilot projects on green hydrogen. And MOPNG has also began a pilot scale gray hydrogen project. I think I have to, sorry, on hydrogen CNG initiative, which is 18% up to 18% hydrogen can be replaced by in the CNG vehicles. So there is a fleet of CNG vehicles and they can easily adopt to hydrogen. So it will also help in strengthening the infrastructure. And another development is that Maharashtra Institute of Technology, in collaboration with World Peace University, plans a hydrogen research center at Pune to achieve carbon neutrality. So these are some of the success stories of India. Only the last part is of my presentation is that how the nations are responding to the hydrogen challenge. For example, USA has announced $8 billion dollars for create four hydrogen hubs, out of which one is to be blue and one is for green, at least. The others may be whatever. Then EU has also published a strategy report for climate neutral Europe. UK has planned 4 billion pounds investment by 2030 and has announced competition to develop hydrogen as a super fuel. So they have huge competitions. And then India on August 15 allotted rupees 25 crores in the budget for the in hydrogen energy and announced national hydrogen mission while commemorating 75 years of Azadi का महोत्सव, Amrit Mahotsav. So this is it is, and then finally let us see ki how India. Normally we feel that India does not have a climate policy or how it is we are transitioning to a policy. Its process began in 1997 with Kyoto Protocol, when India was exempted from taking any action for reduction of emissions. So only database were required to be created and shared. In 2005, the common but differentiated responsibility policy took shape, that it is a common responsibility to mitigate, but action is differentiated. There will be the action to be taken will be different by the countries, like those who are developing exempted or whatever. And then Paris Agreement on climate change was actually happened because the exempted countries were already committed their INDCs. Because when Secretariat asked for commitments, what you can do, so you have already given a commitment, so you cannot be exempted. You have to take action. And COP26, India's Panchamrita was stated by our Prime Minister, and then launch of green hydrogen policy. So you can see very rapid progress is taking place in last 5-6 years about the climate policy. And what is Panchamrita? I think I can skip that. Yesterday has been talked about, and there are 5 goals as such. And the last is the National Green Hydrogen Policy, which has been announced. And by the Ministry of Power. And it says hydrogen and ammonia are going to be the future fuels for replacing fossil fuels. Set it out, I mean, for industry, ammonia, we at least, and for hydrogen in transport sector and industry, agriculture can also be benefited. And set a target of production of 5 million tons of green hydrogen by 2030 to reduce dependence on fossil fuels and also reduce imports of crude oil. India has to emerge as an export hub. It identifies the mechanism, the policy identifying mechanism for transmission of renewable energy, because we have to use renewable energy for production of green hydrogen. So it is very clear guidelines for transmission of renewable energy, regulations for environmentally sustainable energy security of the nation. So this policy is basically to make it India as a hub for the future. So and some questions still remain to be answered. Partly we have tried to answer some of the question. Can hydrogen be widely used as an important fuel for the future energy transition? How green is green hydrogen? That's also a question. How green is blue hydrogen? Many studies have shown how green is blue hydrogen, that you capture, whether you capture CO2 or not, but can it be treated, how much during operation? Then why there is IPCC urgency to scale up hydrogen technology worldwide? Because IPCC report specifically mentions that it should be scaled up. And which processes for hydrogen production should be considered leading to green hydrogen? Can be added other than electrolysis? What processes should be intensified for producing green hydrogen in the country, within the country? So, and of course, some of the electrolyzers are coming in the big companies being set.
Changing. Right. Okay. Namaskar, uh, all the delegates and the participants. First of all, I would like to thank Alti ma'am for inviting me and giving me this opportunity to express my views on this hydrogen production and all this discussion on this hydrogen production and storage and transportation and other things. So I'm Sanjay. As Madam said, like I'm a faculty in the Department of Chemistry, IIT Indore. So I basically work on catalyst and the catalytic process development, and primarily for hydrogen production. And along with hydrogen production, my interest area is biomass valorization and carbon capture and its utilization also. So I'm going to discuss about hydrogen production partly here. And in my presentation, you'll see initially some of the background, like already Madam and the previous speakers has put forward all the background of this whole discussion on hydrogen. And you may find some overlap of slides also. Please excuse me for that. And in the later part of my presentation, you will see more chemistry part of how the different processes of hydrogen production can happen particularly from the liquid hydrogen carriers and liquid organic hydrogen carriers. Okay. So previous speaker has already discussed about this, but one important question is there whether we have really an energy crisis in the world. So the answer is no. But why we are looking for different alternative processes? But that is, as Professor Yadav has mentioned yesterday, like one of the driving force is how we can take care of our Earth. So basically, it's the carbon emission that is driving this whole development of exploring different type of energy sources. So if you see, India has already promised like by 2070 India will achieve and the net zero emission, and this is also primarily because India is the third largest the carbon emitter, and primarily if you see in the pie chart, like almost 60%, over 60% is carbon dioxide is coming from fossil fuel, and that is also because world is heavily dependent on fossil fuels. So that is the major problem. Okay, and along with different contributor to this CO2 emission, if you see, the transport sector is one of the major contributor in this whole carbon emission. And India is working pretty good in this range. Like we have been using 5% ethanol mixed petrol, and recently like 15% methanol mixed petrol is also coming up, and several CNG and natural gas vehicles are there. And the alternative fuels could be biofuel and electricity for EVs. So ultimately, like we can explore different of energy sources or alternative energy sources, but we have to see in the holistic view like how much carbon emission is happening there. So that is the catch point here. So in this particular figure, you will see like different modes of transportation, right, from walking to our luxury car. So okay, so okay, why is this going down slow? Okay. So this particular section, like we all know that we should use public transport, and that is primarily because the black balloons indicates how much of the CO2 emission per person per kilometer travel. So you'll see like in all these public transport, there is a per person per kilometer traveling, the carbon dioxide emission is less. But the interesting point you'll see, okay, so these two red boxes where both are electric vehicles. Okay, and we know like electric vehicles are running on batteries, and batteries are charged by electricity. But how these two are different, because one you see like it is the second one after means a fossil fuel running vehicle, and the second one is the electric vehicle. Okay, so but you'll see like it is still very high carbon dioxide emission, and that is primarily because how we are getting that electricity to charge our vehicles. So if you see in India or in the global, if you see still over 90% of electricity is being produced by thermal power. So a lot of amount of carbon dioxide emission is there. So it's not just we are using electric vehicle and we'll see like, okay, there is no carbon dioxide emission, but holistically how this electricity which we are using and how much carbon dioxide emission is happening there, that also we should take care in this whole discussion of having an alternative and sustainable energy sources. Okay, despite all these things, India is working pretty well in this sector, and along with this renewable, the solar, and where India is leading the ISA, the I have read some news like there is high potential for wind based electricity also, and recently the first ethanol the flex engine based bus is also launched, and 15% methanol blended. So all these are contributing to reduce not only our dependence on the fossil fuels, also we will reduce its consumption in India, and we can have also an alternative energy source. Electric vehicles, we can see like almost like everywhere we are seeing electric vehicles. As I mentioned, how we are getting the electricity to charge these electric vehicles. But apart from this, there is one other issue, like these electric vehicles are majorly running on the lithium ion based batteries, and in India, literally, we do not have any reservoir for lithium. So it will be a case again, like we are importing fossil fuels from Gulf countries, and when we have all the vehicles running on lithium ion batteries, and then we will be importing lithium from China and other countries. So again, dependency on other countries will be there. So that scenario needs to be changed, and we should become more independent and have our own energy sources, which is pretty much indigenous, and we can fulfill resources from Indian things. And not only the lithium ion resources, but if you see for the electrode, we need nickel and the lithium itself also. These are coming from open mines. So open mines means like, again, the destruction of the natural resources, deforestation, and again, it will cause a lot of carbon emission. So at one end, you'll see like electric vehicles are, there is no carbon emission, but ultimately, if you see the open mine, nickel or the lithium, and so these are ultimately, there will be a lot of carbon emission. And for charging of electric vehicles, again, a lot of the carbon, the thermal power, or the coal-based electricity is there. So it's not that the one system means all of these alternative sources which we have at this moment, all of these have some problem. Okay, so all these verticals have to go together, and they are not competing with each other. In fact, they are complementing each other. So in this backdrop, like hydrogen has been considered as an important fuel of the future, and that is because it is a well-balanced, energy efficient content, and the carbon dioxide free transportation it can give. And obviously, it can reduce our dependency on fossil fuels, and greenhouse emission will be definitely reduced significantly. As I mentioned, like its energy content is quite high compared to the fossil fuel, and water is the only byproduct. Apart from its uses and its impact on the reduction of the overall carbon or the greenhouse gas emission, the major challenge with hydrogen is its volumetric energy density, which is very less. So its storage and its transportation, because being a gas, it is difficult to store. So just to give an idea, like 1 kg of for running a vehicle for 100 kilometers, we need a 11,000 liter tank. So that is at atmospheric pressure, obviously. So all these things are happening there all together. But in the hydrogen-based society, you'll see like 3 verticals are there: the production, storage, and utilization. Madam has very nicely compared different type of production pathway. I'm also going to discuss some of the things. So ideally, a fuel cell electric vehicle, how it is different from the electric vehicles. Only thing that we have here, the hydrogen fuel tanks, and the battery is still an integral part of this the fuel cell based electric vehicle. But only thing is that its size will be reduced, because the one of the major problem with the fuel cell or the hydrogen based vehicle is that it cannot give a sudden thrust when we require. So that's why the battery backup is essentially required. At the global front, you will see a lot of progress has been observed, and this is a picture from the Toyota Mirai, and Hyundai Nexo is there also. And if you see, yesterday also, Professor Ghosh has discussed about like how is the fueling time. So if you see that it is quite comparable with whatever the current infrastructure, and we are using the petroleum based compared to the electric vehicles. Here everything is compared with the electric fueled vehicles, which is currently facing challenges with the time it takes to complete charging and other things. So, but the major problem with hydrogen is still we have very poor infrastructure, and that's how it is still evolving, and the cost of the hydrogen-based vehicles are very high at this moment. Despite that, there is a projection that worldwide the infrastructure of hydrogen is going to rise, and this blue bar indicates the Asia Pacific. Particularly, it also includes India. So in worldwide, everything you can see there is expected to have a very good infrastructure. It is going to be going to progress. Okay, these are some of the glimpses from already running the hydrogen fuel station, and you'll see like there is no difference between what we are using the petroleum based the fueling stations. So everything looks same. And so hydrogen is used almost in all the sectors, like being it's a small vehicle or the heavy duty trains. This is from Germany, and the plane or metro or the heavy duty trucks. So in almost all the sector, it has potential, but essentially people are advocating that the smaller vehicles should run on battery based systems, and the heavy vehicles should run on hydrogen fuel, because for the storage of hydrogen also we need enough space. So that kind of space can be provided by these big vehicles. Probably. So in Indian perspective, if you see, like I could find like 3 examples. Like very recently, KPIT developed this fuel cell based hydrogen fuels, and I think on 10th they are going to present something also. Some of the news details I got, like the toy train in Simla is also going to be in the hybrid mode, the fuel cell based system, and this is a Tata based in Leh Ladakh. They have tested this hydrogen fueled bus. Madam also discussed about this the HCNG. The important part here, like if you see how much it is reducing the overall carbon, see 70% CO emission can be reduced by 18% SCNG hydrogen blending in CNG, and for the overall greenhouse gas emission can be reduced by 15 to 20%. So that is also because it's not just hydrogen can be used in the fuel cell, but we have to find like how other ways can be utilized by using hydrogen, so that ultimately we can achieve this reducing the carbon emission. So in all these things, the projection says that hydrogen demand is going to increase in almost all the sectors. But you know, like hydrogen is everywhere. It's the most abundant element in the earth, but it is nowhere because we need hydrogen in the form of molecular hydrogen, H2S. So it's Earth in atmosphere, it is less than 1 ppm. But if you see like almost all the organic molecules, they have like CH bond. So H is there, but how we can recover this H which is combined, chemically bonded with a molecule, so in the form of hydrogen molecule. So I'm going to discuss those things. And if you see in the industrial level, a lot of processes are already established and being explored, like ammonia cracking, the thermocracking of methane, or the methanol reforming, water gas shift reaction. So all these processes, they can run, and they are already well tested processes. But if you see, like in the water gas shift reaction, there is a, for each molecule of hydrogen gas, there is a one molecule of CO2 is also being produced. And similarly for methanol reforming, there is, for two molecules of hydrogen, one molecule of CO is also produced. So we have to find out, because ultimate goal of exploring hydrogen as a clean fuel is that how hydrogen is also produced. That is also a very important thing to discuss. The type of hydrogen has already been discussed by all the previous speakers. Okay. So ultimately, if you see this brown hydrogen and the gray hydrogen, which is high carbon emission. So in terms of carbon, like blue, which is similar to gray, only that we have a carbon capture process integrated with the production. So whatever carbon dioxide is generated, it is not being released in the atmosphere. It is stored, or probably it is utilized. And the green hydrogen, where there is no carbon is involved at all. The challenges with hydrogen, as I mentioned, because of its low volumetric density, its storage is a big challenge. So whatever hydrogen is being stored or utilized in all these vehicles are at 700 bar. So you can understand, like hydrogen, which is considered to be a flammable gas, and you can store hydrogen at 700 bar. It is still like pressure and flammability, and then all these things make it more dangerous. So we have, and people are working on reducing the pressure. And the another challenge is the designing of the container. We can use like CNG containers, which we already have, like it is well proven. And that is also because chemically hydrogen can penetrate the CNG walls, and then it can lead to the cracking of the cylinders. So specially designed or specially lined this kind of containers are required for. So a lot of R&D is required even in the designing of these containers. People, I guess, like in IIT Rupert, people are working on this. Also, there should be some awareness, like hydrogen is equally or even much safer than petrol. So that kind of awareness is also required to utilize hydrogen as an efficient fuel. This slide indicates like the different type of hydrogen storage material. Primarily, these all are solid hydrogen storage material. You can see here in the red squares, and some of the gaseous form of hydrogen, which is stored in the porous materials. But the interesting part is which is under this the black or the red dotted box, which is the DOE target. So which indicates like there should be a deliverable, the hydrogen absorption and the delivery hydrogen temperature, and how much the hydrogen capacity is stored. So everything needs to be well balanced. Like it should not be like the hydrogen storage means like it should be reversible. So it should be able to store hydrogen, and when we require, it can be easily released from the hydrogen or from the storage material. So those kind of materials are called hydrogen storage materials. In this chart, it is a more simplified form of. So here the volumetric capacity and the gravimetric capacity of different type of hydrogen storage, the complex hydrides and the chemical hydrides, and the pressure tanks like 700 bar or 350 bar, or the liquid hydrogen at minus 285 degrees Celsius. So those things are compared with these liquid organic hydrogen carriers. And you can see like many of these liquid organic hydrogen carriers, they fulfill the primary DOE target of in terms of volumetric and the gravimetric capacity. So ammonia, indeed, it's a future fuel, like because being a carbon-free molecule, so it has the capacity in terms of like high hydrogen volumetric and the gravimetric capacity. So, so liquid organic hydrogen carrier or liquid hydrogen carriers are primarily compounds which can release hydrogen. Okay, so whenever required. So this is what we call the dehydrogenation, and when we to hydrogen, it can be hydrogenated again. Sorry. So primarily it occurs in the presence of a catalyst. And when we want to store hydrogen, so it can be hydrogenated and it can be converted again. So this looks simplified, but it depends on what kind of liquid organic hydrogen carrier we are using and what is its chemical behavior. So it all depends on that. But in principle, it is possible. So as I mentioned, these liquid organic hydrogen carriers, being liquid, is storage, is transportation, and it's dispensing, like the petrol we are using. So we can do it. And the one of the important thing is the on-demand hydrogen production. In few of the cases, we can do on-board hydrogen production also. Like we can fill the tank with any of these liquid organic hydrogen carriers, and then on board we can generate hydrogen and it can be supplied. So principally, it is possible. More things needs to be explored in this direction. So in this slide, like I have just compiled the different system which I am going to discuss today. The hydrogen, methanol, and aldehyde, glycerol, formic acid, ethanol, ethylene glycol. Ammonia, just one slide, like I have compared, but because I have not worked in this system, but this is a very new thing. But in this slide, like the hydrogen can be released from ammonia. At present, it is at very high temperature, 600 to 1000 degree. Primarily, nickel is being used as an important catalyst for this. But because of some of the adverse physical and chemical properties of ammonia, like its thermal expansion, high vapor pressure, and its reaction with the water, so makes it difficult to handle, and also it's toxic. Its vapors are very toxic. The another thing, like the PEM membrane, it cannot tolerate ammonia. Even a very small ppm level, means 0.1 ppm is the requirement. But like when you generate hydrogen at this temperature, and where even at the atmospheric temperature, the ammonia can vaporize. So there will be a lot of ammonia contamination will be there. So even at 900 degrees Celsius, you can see 1500 ppm contamination of ammonia is there. So, but the target is 0.1 ppm. So PEM may not be utilized, or the process needs to be developed in a different way, like there is very less ammonia contamination, or different type of other the fuel cell systems can be utilized for ammonia based hydrogen. So when I was doing my postdoc in 2008, so I was in Japan. So I was introduced to this system, and my boss asked me, like, people are working on hydrogen, and he was working, in fact. And so the task given to me is to release hydrogen from hydrogen. Hydrogen, if I say, it's a very toxic. Okay, it's extremely toxic. It's carcinogenic also, and it spontaneously explode and neurotoxin. So it's very highly toxic system. But at the same time, it is very attractive hydrogen system because it is zero carbon hydrogen source. So hydrogen, if we talk about hydrogen anhydrous, so it is very toxic. But if we combine it with one water molecule, then it is liquid at atmospheric temperature and the pressure. Okay. So as I mentioned, like with one water molecule, we call is hydrogen monohydrate. So I use this system, and then if you see, like it has a hydrogen content of 8%, and it can release nitrogen, which need no recycling, but its recycling can be done. And as I mentioned, like it is a liquid, so it has its own advantages. But how hydrogen can be released? So hydrogen decomposition happens with the two pathways. We call it the complete decomposition, where had two molecules of hydrogen with one molecule of nitrogen. The incomplete pathway includes like nitrogen and four molecules of ammonia. So if you see in terms of thermodynamics, so incomplete decomposition is more favorable compared to this one. So we have developed several catalysts, so which can selectively facilitate this pathway where only hydrogen is being produced. If you see the overall pathway, the production or the cleavage, so primarily both have the similar species. If you see, like this is for the hydrogen and this is for the ammonia. Sorry, this is for hydrogen complete and this is incomplete pathway. So initially there are similar species are generated, but ultimately here in the incomplete pathway there is NN bond cleavage happens. However, in this process, NN bond cleavage not happen. Only NH bond cleavage happen, and then on the surface there will be a lot of H add atoms. They can combine and then release as the hydrogen gas. While when we have NH2 species over the surface, it can combine with H add atoms and form ammonia, and the N atoms they can combine to form nitrogen gas here. So chemically, process is like this. Okay, so in this process, like primarily the NH bond cleavage and the subsequent release of the hydrogen gas and nitrogen gas is released in this whole process over a catalyst surface. So we explore different type of catalysts, and these all hydrogen gas processes happens at room temperature in water. And you can see here like three categories of catalyst we found, like cobalt, nickel, Fe, palladium. They are completely inactive, while cobalt, ruthenium, iridium, they show only 7% selectivity for hydrogen gas, while rhodium gives 43% selectivity for hydrogen gas. So these are the gas evolution pathway. So you can see this whole how much gas is generated, and this is the time profile. So to find out some of the analysis we performed, and this is for the gas analysis. And gas analysis, you can see indeed there is hydrogen gas, and primarily if it is complete hydrogen production, so that hydrogen to nitrogen ratio should be 2:1. So here it is 1.3. It means like there is some ammonia formation happens, which is indeed identified by 15 and NMR. So you can see ammonia peaks are also there. So primarily you can see ammonia is there, little bit of nitrogen, and some hydrogen is also there. So the second challenge was to completely convert, and then what we found, like when we combine it with nickel, forming an alloy composition, so with a specific ratio with rhodium 4 and nickel 1 component, so complete hydrogen, complete selectivity for hydrogen observed. Similarly, you can see in this graph, like it is the platinum content. As I mentioned, like nickel and platinum both are inactive. So when they combine in a specific ratio where there is 90% nickel and 10% is platinum, so it can also give 100% selectivity for hydrogen gas. And you can see here in this graph also, like the mass profile for gas generated and hydrogen to nitrogen ratio was 2, and there is no ammonia formation happens at 280 ppm in the 15 NMR. Similarly, like iridium based catalyst was also found to be active, because iridium itself is 7% selectivity towards hydrogen. Nickel, as I mentioned, it is inactive, but when they combine in this 90 nickel or 95 nickel with iridium, so it gives like 100% conversion. So ultimately, the NH bond activation happens over nickel. However, there is not lot of amount of energy is required to release the H atoms in the form of hydrogen. So those noble metal in even in the smaller amount, they help in the hydrogen H atom spillover. Means like H atom was formed over the surface of nickel and it will spill over to the non-noble metals, and where they can recombine and release as hydrogen gas. So a smaller amount of noble metals help in the facilitating this hydrogen production even at the room temperature in water. Okay, some of the molecular catalysts which we have also worked on, and what we found, like when we have a protic hydrogen like OH, which is a protic hydrogen, it facilitate in the formation in the release of hydrogen. I'll come to the maybe this, and in this profile you can see when hydrogen combined, and then this O negative, it helps because it can facilitate the protic hydrogen formation. And in this process, when you see it's H at which is coordinated with the ruthenium, which is hydridic hydrogen, and H which is coordinated with oxygen, which is a protic hydrogen. So the combination of hydridic and protic hydrogen released as a hydrogen gas, and then this catalytic cycle completes, and then again it combines with hydrogen, and then activation of NH bond and facilitates this whole process of hydrogen production even from the molecular catalyst. I mentioned like nitrogen recycling is not required, but bond hybrid process is well known, and there are different other processes like electrocatalytic processes, electrolytic processes where nitrogen can be reduced to ammonia, and the other processes like directly into the hydrogen is also there. So quickly moving to some carbon-based systems. So lesser will be the carbon in the source, there will be lesser amount of carbon dioxide emissions. So that is the main motive. And methanol is being used as an important source for hydrogen production, but that is, we all know, like very high temperature is required methanol reforming. So methanol, it has very high hydrogen content, 12.68%. Again, it is liquid, so it can be easily stored, it can be transported easily, and there is no carbon-carbon bond cleavage is required. So lesser amount of energy is required to release hydrogen from methanol. What happens? Can you move to next? Okay. It's taking time. Where is the sensor? Sometimes it's difficult. Okay. So methanol reforming, as I mentioned. Okay. Quickly. Okay. So it is happening at 200 to 350 degree Celsius. And if you see in the process, up to ammonia, the formic acid production it is not much favorable. However, ammonia to the formic acid to hydrogen is more favorable. So we try to find out different catalytic systems where the low temperature hydrogen production can happen from ammonia, from methanol, and the catalyst can be inexpensive to the other catalyst, and there will be more selectivity towards hydrogen. There will be no carbon emission. Whatever carbon dioxide material are there, it can be extracted in a form of different molecule. So overall process of this methanol to hydrogen production involves, like methanol first release one molecule of hydrogen to form formaldehyde. It reacts with water, and with the another molecule of hydrogen is released to form formic acid, and formic acid further dehydrogenate to hydrogen and CO2. So if we cut down this process here up to formic acid, then there will be no carbon dioxide emission. So this is what we tried to find, and with the different type of catalyst we explored, we found like ruthenium active catalyst, and when we combined ruthenium with a nitrogen donor system, so basically the nitrogen facilitated in the coordination of methanol, and we could achieve only the formic acid formation. There is no carbon dioxide emission, although little bit of the reaction, the byproduct was formed. Okay, so here you can see different type of ligands was explored, and we found like these ligands are indeed facilitating the gas generation, and the efficiency of the catalyst was increased. Here Even in the profile, you can see without ligand, it is lesser than 250 ml. However, in the presence of ligand, the larger amount of gas was generated. As I mentioned, there is indeed a role of nitrogen gas. So this is the XPS profile. And you can see the nitrogen is indeed present. Overall, there is no much change in the overall the chemical environment of the ruthenium itself. Okay, here you can see this is the 13C NMR, and you can see only format is formed. So as I mentioned, like the byproduct, the main product was the format, and the hydrogen is the only product. So you cannot see any carbon dioxide emission, although there is some carbonate formation happens. But if you compare here, it's very less. So we are still working on this process, and this process we have also patented. It is granted also. So we tried to explore this applicability for long-term bulk, and we have, because I'm a chemist, so I work mostly on this glassware, so I have my own limitation. So here you can see like almost like 2 liters of gas was generated from this process, and we compared it with the literature known systems, and what we have found, like 1 kg of hydrogen can be generated from 13 liters of methanol, and there will be no carbon dioxide or contamination we have found. So and the most importantly, it can be done at 130 degrees Celsius. So it's quite less, because compared to the methanol reforming processes, which happens at 200 to 300 degrees Celsius. This process can also be explored for other type of alcohols, like we explored it for ethanol. We are still working on that. But primary results at 110 degrees, 1 kg of hydrogen can be generated from 40 liters of ethanol. This is based on the initial results. The formaldehyde, also the second component, it also has a very high hydrogen content of 8 to 8%, and aqueous formaldehyde is a important, it's a very common chemical in all the chemistry labs. And here we also tried to explore some molecular catalysts, although these processes are done to study the overall pathways. So what you can see here, in the presence of different ligands, the processes, there are different ways of, or different profiles of gas production happen. And this indicates that different type of species are involved in the process. And here in this, the hydrogen to CO2 ratio indicates like initially there is high hydrogen content. Later on, there is the hydrogen to CO2 ratio comes down to 1, which indicates that this formaldehyde initially releases hydrogen, and then once formic acid is formed, so formic acid also releases hydrogen and CO2. So that's why ultimately there is the high CO2 content, and the hydrogen to CO2 ratio was reduced. Okay. So in all these cases, we always try to find out what is its applicability and recyclability of the catalyst. So this catalyst can be recycled up to 8 cycles. And so 1 kg of hydrogen can be generated in 37 liters of aqueous formaldehyde at 95 degrees Celsius. So these are the assumptions, and we formed based on the processes we developed. Formic acid also, like, although it has a very less hydrogen content of 4.4 hydrogen weight percent, but it is liquid again, and it can be easily transported. The major problem is that we cannot restrict it to something like it. There will be always a CO2 gas formation with 1 molecule of hydrogen produced. Okay, coming directly to this process. Okay, some of these processes we can see here. This protic hydrogen and hydric hydrogen presence is important in all these processes. I'm just skipping some of these things. Maybe. Okay. Please excuse me. Okay. So glycerol, the glycerol, we know like it is a byproduct of the biodiesel. So and it can be converted into different type of processes or different type of products, which are very valuable product. So and the lactic acid, which is one of the important component, which can be converted into polylactate, and which is a biodegradable polymer resources. And so we developed a process where this glycerol can be converted into lactic acid with the release of hydrogen gas. And this hydrogen gas is a completely pure hydrogen gas. There is no other contamination of carbon. And and this process, what we have observed, like 52 liters of glycerol is required to generate 1 kg of hydrogen. So 1 kg of hydrogen is almost 11,000 liters of hydrogen gas at 110. At the same time, there will be 64 kg of lactic acid will be also produced, which has its own commercial value, like 160 rupees per kg of lactic acid is also. The last slide, like I think Vasmiji is also going to discuss about it, but the PET bottles is a major problem. Like only 17% of PET are being recycled. Almost means the rest are going into landfill, and there is a challenge in recycling because we cannot always recycle it. So we try to find out a process like where we can convert these PET bottles in one pot into hydrogen gas, and we can get the constraint of these the PET bottles, and so that it can be utilized in the formation of the new PET bottles. So if you see the overall process, it has the structure. So it has terephthalic acid and ethylene glycol. So in the pot process, we transform these PET bottles into hydrogen gas. Okay, and at 160 degree. I'm just clicking. Okay, so 1 kg of hydrogen, we require 33 kg of PET bottles. So it is a one pot process where we can just cut the PET bottles, the flex we can put in the reaction vessel, and we can generate hydrogen gas, and the terephthalate and the formate can be extracted. There is no other gases, like it's pure and 100% pure hydrogen gas is produced. So with this, I would like to say, like, green hydrogen is, of course, is an important thing, like where there is no carbon involved. But by changing or the tuning or with the intervention of the chemical technology, we can put all these methanol, ethanol, ethylene glycol, the low carbon based systems in between the green and the blue hydrogen system. So with this, I would like to thank everyone, and these are my group members. Okay, thank you.
Any questions? Huh? Though we started really late today, so we are.
As scientists, of course, you are making lot of experiment and that estimate hydrogen can be created wherever hydrogen exists. But have you studied that when can be is converted into a commercially viable and in a quantities which are required in the country? The amount of hydrogen required in the country is very huge.
Yes.
So, and the cost involved.
Yes.
They are the. So, whether any such study has been done, so you've shown, I've seen that wherever hydrogen exists in that can be removed from there. I think that's extended. But whether it is really viable to create the hydrogen,
I think like
quantitative can be
Hand
Yes.
mic, you know.
So see, I'm a chemist, so I didn't do much thing. But whatever based on the initial results, like because these processes, whether the reforming or the steam reforming processes, they are there already there, And if you compare the other parameters, like if you consider like methanol only, methanol reforming process, it happens at 200 to 250 degrees Celsius. So this whole processes, and if we can do the same reaction at lower temperature, then definitely the cost can be reduced significantly.
So this is done.
Huh.
First of all, the raw material, you're converting from methanol to hydrogen.
Yeah.
One has to see that methanol must be available in the country.
Yes, yes.
ये वैसा problem है ना कि
Yes.
Resources.
Power station.
Yeah.
We don't have the uranium, so the development of nuclear is going down. And the other process is not developed. So whether such and methanol is available in the country in such a
So methanol can be produced, sir. Like
is produced.
yes.
An assessment of I thought Malti can we give this project to one of the scientists who are with
Niti Aayog has a big scheme of methanol production.
Yeah, methanol
Program
economy is
from
already there. Like, and
Yeah.
But then you remember that coal liquefaction and conversion of coal long ago the project was started
yeah.
with the UN assistance. But finally it is dropped, nothing came out of that. But now is the need because it is a commitment that 2070 we should be carbon free.
Yeah.
So then that yesterday's paper was also giving the idea that hydrogen can be created with so many ways. Anything can be converted into hydrogen, whether it is a plastic or a
Because carbon and hydrogen are in every chemical.
But can there be a process which can give us hydrogen quantity?
I think one important question which one of the things we raised was that can blue hydrogen be treated as green hydrogen? So partially, I think your research has answered that if we have, we can do it to some extent. And so that is one thing which in my opinion comes out of the research. And
Sir, to answer your question,
The research is there, and research has been there everywhere. You go to IIT Engineering College, the library is full of research projects and PhD degrees. But you know, one can get a PhD degree. There are so many people here. This PhD remains as a thesis in the form of a book lying in the library and not converting into the practical usage in the country. And the one main idea is, I'm not saying that these are useless, but it is training a mind for research projects. The input of that research project is not very practical, and therefore the output is also. So when I was in CERC, there were so many people approached that the real actual information, correct information is not available to them. They go by some information. Therefore, whatever results they get, they are rated not practical, but for the point of view of research, it is okay. So we issued a direction to POSOCO that any student approaching them for research job from IITs or engineering, give them the information so that input is right, output will also be right. So in that context, this is a very timely discussion you have arranged. But I thought our outcome of our discussion should be that yes, we can be carbon free, and there is a process available when hydrogen can be created in the huge quantities we need. I mean, there are the whole other areas are there, but there is a power sector requiring total, the amount of we consume.
yes.
600 million tons per annum, more than that. So we have to replace this. But Mr. Shahi was saying it doesn't mean that we have to eliminate this. There are
So
other compensatory processes are there, but still the amount of problem we can envisage is a huge. So from that angle, I was thinking you must
Yes,
answer
sir.
that
Sir,
question.
actual main problem is that because I am working in academia, like I can understand like there is a big disconnect between industry and the academia.
Right.
So we do not know what industry want, and when industry comes, so they always talk about economy. Like, because many industries have contacted me and they ask like, what is the economy? How much money they can make? So then
Yeah.
there should be a good nexus is required, like not only from the industry, academia, and the government body. So there should be a common consensus. Based on that, they should work in an integrated manner. Currently, they are working very scattered manner. Like, so
I
that
agree
is
with you.
major problem. With all these processes which I have discussed also, it has potential, but I have my own limitations. But at the point where I have ended my experiment, someone from the industry should take up, and then they can evaluate these processes and they can give us the recommendations. So you work on these things, and to miss what are the other parts which industry looks for. So then these processes can be taken forward, obviously.
I remember IIT Kanpur developed a solar cell, which was very economical, but no industry picked it up for further development and production. And we went on importing from China, and in a large
Industry
quantity.
look for like importing. I think importing technology from outside is a very easy way because it is well proven,
Yeah.
well tested process.
That's right.
So taking risk is also important because otherwise you keep on importing technologies from outside.
Yeah.
So Indian technologies, because what I have discussed about the hydrogen production. So I got 5 patents. I was discussing with Varshniji. So I got 5 patents, and it was now it's the property of Japan government. But I worked there. So their industries are ready to work because all of these processes which are industry oriented, industry immediately picked up. But here we are lacking. Like
Now it is changing. The
Yes,
government is
changing.
trying to
yes,
incentivize.
Malti, my point is, for example, hydrogen.
So it takes time, but it has this question has been there for years together. Actually,
Hydrogen is required in a power station for injecting into the water for
yes.
neutralizing this oxygen. But that hydrogen, the hydrogen which we procure from the market is very expensive.
Very expensive. Yes.
If that is very expensive, and we need very small quantity, because the oxygen in the water has to be removed
Yes.
from the corrosion point of view. And we are discussing that hydrogen can be converted to hydrogen, of course.
I think we break for tea and have continued discussion there, if you permit, sir.
But the answer of this should be found out.
Yeah. Yeah, because there is
When
a
industry
startup
people
session
will-
tomorrow.
The
Let's
young
see what.
children, we look towards you for the answer to this. Yesterday you were saying, I think, you are doing some PhD.
So there is no answer, but actually a question to your extent. Sir, as most of the processes you mentioned are endothermic processes, so under normal circumstances, the Gibbs-free energy change of all these processes will be positive. So where is the spontaneity to these processes?
Yes, because the involvement of catalyst is important in all these processes. So that's how it is progressing in this form manner. So catalyst involvement, that is there because if you see like all these processes, the high temperature is required. So those are probably the different processes where there is no catalyst are involved, but with the involvement of a catalyst, the processes, the condition can be bring down.
Do
So-
you want hydrogen to release spontaneously from the stored chemical?
No, sir, but there must be a
That is why
there must be an exothermic process, no?
No, but we cannot change, no, like.
For
that is
perfectly
the inherent property of
exothermic
For
process.
the formic acid, you are doing hydrogen and you are transporting in a pipeline.
And
Do
then,
you think it would be advisable if spontaneously hydrogen leaks out from that? So that is
Yes.
why
So-
it has been made like
And
that.
that's again a problem rises of liquid hydrogen.
no, liquid hydrogen
Because-
is a totally different thing.
Yes.
So because why they are making it liquid? Because means what Japan is doing, they have hired some land in Australia and they are generating hydrogen there. They're liquefying it and bringing it in ships. So this is what they are doing. But this is a mean of transportation, like transporting liquid is an
She is
easy
in
task.
Nagpur.
compared to-
Liquid
So Dr. Ahmed will be speaking now.
Okay, so thank you very much for Very nice introduction, which I don't deserve.
No, no,
I'm
it was
still
not
a
nice.
student. I'm
Short,
still-
brief, very brief.
Well, for last 15, 20 years, I have been trying to understand a little bit about, intelligent materials. That has been my passion. Being basically electronic engineers and semiconductor technology, hardcore, working there for more than 40 years, I tried to switch over to the life sciences and start looking at the relevance of nanomaterials in biomedical applications. You'll be surprised, but there is a history behind that. Anyway, so in this context, I came across different forms of materials, starting from nanoparticles, then nano cores, nano stars, anything I add to that in any shape, size, morphology. And today the situation is that there is no end that what kind of morphology you want, you can get it. Chemistry is well developed and it is known. Now, that day we had a little chit chat and she asked that, do you have anything on hydrogen? I said, well, I have been not directly doing that, but I'm interested in that. I'm trying to understand some of these things so I can share my views and learn from others and try to tell something what is going on recently. After the discovery of this graphene, let me tell you a little bit of background. This poor graphene was unknown for 4 centuries because of a simple mistake of a physicist that predicted that graphene is not possible to separate from graphite. And the experiment which was done, very, very rudimentary. Somebody in Manchester University took a piece of graphite and took a scotch tape and started, removing, if possibly, sometimes some layer, and they got it. One monolayer thin carbon hexagonal lattice of graphene was discovered, and in 2010, it fetched Nobel Prize. And since then, the materials of this two-dimensional nature are picking up like wildfire. Nobody knows where will it go and what it will do. Now, without going into this, it's a very big, vast topic, and we cannot finish things in one lecture. So when Madam asked me, Madam Presidentin in German, so she asked me to give a lecture. I thought, why not I look at the role of these catalysts? Can this two-dimensional material play a significant role in splitting hydrogen from water? Very simple. If you look at all the processes, what people have been talking about and what people have been discussing very passionately, they have worked for years together. Everywhere, the vehicle goes there where it comes to the low-cost catalyst. If catalyst is not low-cost, then what Professor was telling, that why it is not practically available and why it is not going to be trillions of tons of hydrogen required by the world. It is true. If we don't hit the problem at the right place, then we can do little chemistry here and there and modify molecules, and from any source you take, you can get hydrogen by following some chemical need, which is not indeed any demeaning thing, no. But the problem is so gigantic that the method also has to be done in an equally gigantic way, and it should produce hydrogen for our requirement. Please, next page. No, go back to. Now, we have two basic problems. Globally, if you look at, that is reduction of carbon dioxide and production of hydrogen. If you hit these two problems, and if you hit it simultaneously, then you are still better. Now, I am trying to give something where possibly it can be done both together. That is, convert carbon dioxide into useful molecules, as plants do, and produce hydrogen so that it can be used as source of energy. If you go to the next one, I don't know whether it is visible, it's too small. See, if you look at the fuel value, hydrogen is at the top. And that's the reason that why we are looking for hydrogen. There is no other reason. It is one of the simplest element in the periodic table to start with. And it is immense source of energy. Forget about other elements in periodic table. Hydrogen itself in combination with oxygen and nitrogen has created almost the whole universe. So if we understand how hydrogen can be manipulated with the help of a low cost catalyst. Now, when it comes to catalyst, if you want low cost, why do you go to anybody else? Look towards God. God has given enough sunlight, immense source of energy, right? Photons. They're just falling, bombarding the whole earth. Now, if we take a catalyst which is initiated by the photons emitted by normal solar radiation, our job is much better because we don't have to go for something very expensive. Fine. So, a catalyst should not be only a catalyst chemically, it should be a photocatalyst. And photocatalyst means the moment photocatalyst comes into picture, that is, solar light is falling on a material. And material is what? Conduction band, valence band, separated by a little band gap that is called semiconductor. Now, if solar light falls on it, few electrons from the valence band, they go jump to the conduction band. As far as it is concerned, it's very simple. Everybody knows it, and this is OJ process, and this is done. Now the story starts after that there is excited electron in the conduction band, hole in the valence band, that is vacancy. Now they will move in opposite direction. But unfortunately, it is so that very quickly they try to recombine and finish. So if you want to use this light as catalyst, photocatalyst, source of photocatalyst, you should have a material which is of a semiconductor nature where the band gap is such that, first thing, total entire solar spectrum should be sensitive to the material so that you don't leave anything, any energy, and use all the solar energy and generate electron hole pairs. So the next problem is how to make use of that, because electrons and holes both are highly reactive. And most of the materials, if you take a look at that, in the valence band and conduction band, in between, there are trap states. So they are either trapped, they are detrapped, all kinds of things happen. And ultimately, the lifetime, that is, as long as they are free, they are not combining, that has been tried to increase. And solar cell people, they have worked day and night for years together to use this phenomena, that how to separate them and collect them before they recombine. It's a very, very natural process. Now, with the relevance of two-dimensional materials, the technology which was needed to create a situation where electrons and holes are collected before they recombine, that became much easier. And that is what is my basic theme of this lecture, that how we can do it. If you look at the graphene, it is a monoatomic layer of carbon hexagonal lattice. All the properties are calculated, theoretically, experimentally proven, characterized. It's a zero band gap material, no mass of the electron at the Fermi potential, and it is unique. It doesn't switch off. Even if you remove the electricity, it doesn't switch off. So people initially thought that they can make FETs with very good switching properties, and this will be ideal material. This is going to replace silicon technology wonderfully. But this drawback stopped the whole work. Of course, that has been conducted and many things are coming. Now, a cousin of graphene was discovered by replacing 4 nitrogen atoms into the hexagonal lattice of carbon. And that was named as graphitic carbon nitride, G-C3N4. And this is such a robust semiconductor where band gap can be changed, position of the conduction band, valence band can be changed, and other structural properties can be changed by putting certain dopants, because there are certain bricks into the lattice, and it is a treasure house of all the catalytic properties which we can imbibe into this material. And it is only 1 monomer thin. So instead of making electrodes of platinum, palladium, are very expensive materials which are not going to last for long, the way we are using them. So it can replace most of them. Now, can you move on? Yeah, still ahead. Please. I have given all these, what should be the energy band gap and all those things. And this photon is converted into chemical energy, and H2O is dissociated into H2 plus half O2, right? Please. Go ahead. I think, yeah, this is graphitic carbon nitride. You see, there are hexagonal. What is the pointer? Is there? Yeah. Yeah. You can see these are hexagonal lattice, right? But in between, there is a break. Generally, as a chemist, one wouldn't like to have this break because this doesn't look symmetrical. It's doesn't look beautiful. It should be continuous and it should be used like that. But the beauty of this material is that this vacancy, here you can put palladium, platinum, gold, silver, anything you wish. And all the properties of those elements combined with the property of this element, carbon nitride, makes hell of difference. You can practically do anything you want. And please go ahead, then I'll show you some of these examples. Yes, sir. Can it? Okay. This one. Oh, I'm poor, huh? Yeah. So here I'm showing This is that lattice of graphitic carbon nitride. And layers, each monolayers, they are stuck together by a van der Waals force. So whenever you delaminate them, they will come out separately, and you can attach that. And when the light falls on it, then these reactions can be initiated at the edges of these band structures. If somebody is interested in the details, I can share with you, because I have tried to skip those things. I don't want to bore you with, mathematics and formula and all that. So I have tried to skip that. So it's a very simple, layered material, monolayer material. You can have one layer, two layer, three layer. Now, beauty is that if you have one layer material, band gap is something. If you put another layer, band gap is changed. If you can make an overlap, it is not fully, covering this, then the band gap will change. So enormous ways you can find to manipulate this material to change the transport properties of electrons and holes, and you can get them, extract them, and produce hydrogen in a very simple manner. Yeah, let us see. Now, if you compare this graphitic carbon nitride mixed with other materials, right? Then you can see the hydrogen production, that is micromole per gram per hour. Then you can it's not interacting. Yeah. So you can see that there is sufficient variation in the production of hydrogen. And similarly, this is compared in the bar graph, same thing. And these are the, SEM pictures of the clusters. These layered materials, they form clusters. And these are dispersed very well in different solvent media. So you can use them and make your reaction take place there and produce hydrogen. Now, how to collect hydrogen, how to prepare at certain pressure, and how it is going to be used, and how it is going to be stored, and how I heard quite a few things raised by earlier speakers. That is not physics, that is technology. And technology has to be handled differently. You cannot handle technology looking at the atomic level processes. So understand the processes. After that, try to find out the ways how to circumvent those problems which you are going to face. So engineers, chemical engineers, material scientists, they have all to work together to handle the problems, and then perhaps your answer will come after that. And it needs a very massive effort. Nature has provided molecules, nature has provided structures. Only thing is that we have to harness them and use them the way we want. So these are the structures at that level, and you can play around with that in a number of ways. Now, how this is synthesized is shown here. Fabrication of this NBCNX. What is that? Complex composites. Yeah, it's another interesting thing, that this graphitic carbon nitride can be combined with graphitic carbon nitride itself of a different configuration, and other materials of two-dimensional nature are nanoparticles put together. And all the properties are synergistic. So you can actually make very optimal condition, provided we run these experiments and we run these theoretical studies together. and find out the best way. Uh, Now, here again, a comparison is given. Well, I have taken from. Now, you see, these it's a problem when we use catalyst. If you do one run, then do 2 run, 3 run, 4 run, many runs it can be used. It's a very important parameter. Here you can see that the efficiency remains practically same at different runs. So reusability of this catalyst is excellent. And this is the basic unit from which this graphitic carbon nitride is synthesized. And I think I have some of these and composites. Okay, let's forget about it. You can make nanotubes. This material can be formed into a nanotubes, something like a few nanometer size, and it provides excess active surfaces for reactions to take place. It can be made as a rope also. Sorry. No. Too fast. Too fast. See, instead of very high cost noble metals, you can use very low cost metals like copper and cadmium, titanium as catalyst, because they are also photocatalyst, and when they combine with graphitic carbon nitride, a lot of opportunities are there, and people have tried to optimize them. Now, I think this I saw in the morning also, this picture of a car where this hydrogen is compressed hydrogen is kept here, and then PEM cell or something like that is used to generate energy and produce hydrogen. Now the challenge is, suppose you want to adopt this technology of graphitic carbon nitride to generate hydrogen on a large scale, massive scale, because it is not restricted by anything like that, then you have to think about durability, process durability, think about stability and efficient recycling. These are the factors which will help in translating this technology to something viable commercially. You have to do that. Better precursors. Precursors also, I have shown only one precursor, there are so many. And you see, the beauty of these two-dimensional material is that if you change the precursor, same material will have different structure, another latitude. So you should not be worried that if you don't get the proper structure, then the precursors are completely exhausted. No, it is based on, for example, if you use urea, then graphitic carbon nitride produced will be something. If you use thiourea, then graphitic carbon nitride will be different. So all these parameters, my friends who are working in chemistry, they can really enjoy to get the combinations and optimize it for low cost production of hydrogen. It is completely open area. It has just started. People have started studying these things. Initially, it was not even practically possible because they were all done by density functional theory and other, theoretical techniques to see whether it is possible or not. But now they have been produced in laboratories in quantity, and this can be put to use. So metal and non-metal doping creates havoc. So you can change the material the way you like and make it more efficient and very, very stable. And optimal hydrogen production and cost-effective catalyst. These two problems are supposed to be sorted out if we use the two-dimensional materials instead of bulk material. Bulk material chemistry is not going to provide the answer to professor who was asking in the morning lecture that how we are going to tackle them. It should be low cost, it should be maneuverable, it should be such that it can interact with other materials and get the desired evolution of hydrogen at high rate. These are the problems which are to be sorted out. Now, this is PEM cell, where you produce electrical energy by passing hydrogen. And these cells are available for running trucks, cars and heavy vehicles. But don't look at the cost. It is horrible. It is so high that it cannot be made that common. Reason is, again, using platinum, tungsten, molybdenum as the catalyst. So if you don't hit there that your catalyst is at low cost, well, this will be a dream only available to certain those who have enough money. Otherwise, energy is there. Just pass. I think I will show you the. Yeah. How could this is a small video which shows the functioning of converting hydrogen into energy. Where is that? Can you run it from there? It's just नहीं, उसी पकड़िए वहां पर अभी ये आएगा, यहाँ पे एरो आएगी to run that video. वही प्ले बटन आना चाहिए. This is the problem of technology, not that user friendly as it should be. No, I was showing that, if you allow this this hydrogen to enter from here, then this will be catalyzed here and protons will go here and electrons will be separated from there and hydrogen is separated. It is a PEM cell. Hello. I'm in a lecture. So this is a very, a simple video which shows that, the bubbles are moving and things like that. Something is coming. Okay, no problem. Can we move ahead? Skip it.
Next slide.
आगे. See? Oh, good. Press it. Unavailable? Okay, don't worry. You can see yourself, there is no problem. Nothing novel. Just pictorial, representation. So what I would like to conclude is that two-dimensional semiconductor nanosheets, these are nanosheets, they have huge potential. Let us not run after the bulk chemistry, rather run at atomic layer changes, which can be incorporated in two-dimensional materials, which is a reality, and using the best kind of photocatalyst from solar energy, no UV, nothing, completely solar energy, and hydrogen evolution is taking place. Use technology to collect it and put it in the proper form, whether you want to generate electrical energy, or you want to run a car, or you want to run a truck, or you want to run a ship. It doesn't make any difference. Once you have source of energy and you apply technology, well, you can find out the solution in a very convenient and cost-effective manner. This is what I wanted to convey. There are a lot of things I have skipped here. If you need, I can give you the details, and I have all those details I can share with you. And it's a very interesting area. My suggestion to the colleagues here sitting in the chemical engineering and chemistry, they must grab this opportunity. I'm a physicist. I have looked at the band structure. I have looked at the heterojunctions and things like that. And being a semiconductor technologist, I know it is very easy to produce. So why to run after something which has got so many ifs and buts? Produce it at commercial scale and enjoy the benefit of that whole thing. Because this needs a very, very massive effort of people from different disciplines. But it has huge potential, no doubt.
You use the word cost effective.
Yeah.
Can you give us some idea what is that you had some estimates?
Professor, I have not gone to that level because, I was more interested in the phenomena of catalyst. And those things are being worked out, but it is too early to predict because most of the characteristic features now they are getting, clearly understood, and people are trying to modify that. Suppose, we prepare this material. Now, there will be some contaminations. So the idea is not completely, ideal.
It seems to be very interesting.
Yeah.
So, I don't know.
And not only that,
Through you to the government, this research must be promoted.
Actually, Madras is doing
not only this, Professor, I'll tell you this remediation, this contaminated water, contaminated waste product, remediation. This is one of the ideal way. You don't need any sunlight enough is there. And water is there, sprinkling water on that, and the whole thing starts taking place. And you just spread these materials. These materials are very tiny platelets of monoatomic layer. And the cost will be very, very low when it is produced at commercial level. So why not we put this effort on a real footing where we can bring out practical systems. And if we enter at this stage, we are nowhere less than anybody else. You cannot say that America has done it or China has done it or somebody has done it. No.
I'm wondering, there is somewhere report that Saudi Arabia has designed an equipment which takes methane emissions from the landfills or from the gas fields, and it converts it into hydrogen and graphene.
It is already.
Yes, as I told you. I'm not contesting that. The chemistry is so profound and so elaborate. Anything and everything you can do. Only thing is that
You one company which is actually doing it.
Yeah. So what is that process?
It is called methane splitting, methane pyrolysis.
pyrolysis. These words are very simple. But if you really want to work on commercial level,
Coal pyrolysis. Then.
And it is biomethane or methane pyrolysis.
and I have not touched actually the role of biomolecules. Professor, I have not touched the role of biomolecules. Now, if you use biomolecules along with that, like microorganism, well, another source where at very low cost is spread it. Yeah, spread it over kilometers and generate hydrogen. Wherever you have a space, you can generate hydrogen. So point is that it is such a vast source of energy.
Plastic energy in it.
Without. That's what I'm saying.
Other it will be energy.
And we will be only using a minuscule of the solar energy which is available abundantly to us. As a matter of fact, we are wasting it. Weather control, temperature control, anything you can think of, microbial contaminations, and plant organisms.
So you mean to say chemical perpetual machines rather than mechanical?
No.
It is
Microorganisms.
see there are certain fungi, there are certain microbes, they generate hydrogen. Now technology has to be evolved where those collections of those things are efficiently done for our purpose. Means technology has to be worked out. Now look at a reactor, right? Bioreactor. Look at a bioreactor. What does it cost? How much energy you waste there?
But why is it not successful?
See, point is that those who know this, they don't know the technology.
Interdisciplinary interaction is missing.
They're completely missing.
Requires nanotechnologist, it requires biotechnologist.
Completely missing. Completely missing. Let me tell you, there are people here in the country who say that I can produce 5 nanometer gold nanoparticle. Whereas the situation is, global situation today is that it is impossible. All said and done, it is impossible. Because whenever you produce 10 nanometer gold, there will be 20 nanometer gold particles, there will be 5 nanometer gold particles, there is a spread. Now, people, they just take one piece and say that I have produced it. No, that is not technology. Just dikhane ke liye, microscope, you just go on hunting, In a wild chase, you go on hunting. And let me tell you, carbon nanotubes and these fullerenes. You take simple welder's 2 electrode machine, right? Welding machine. Put 2 graphite electrodes and some catalyst and make a discharge. Whatever muck comes out of that, you go and search. Any kind of nanostructure you think of, they're all there. It is how good you are that you look under microscope, you look under SEM, you look under TEM, and get few of them and say that, look, this is what, the fellow was that, who got Nobel Prize for that, and he was looking for that. But they didn't come before that. When that poor fellow, Smalley, he prepared that and he got Nobel Prize, then everybody knew that it's very simple. Still, that muck is the best source and cheapest source of producing carbon nanostructures. So, we have to do some engineering. We have to attach numbers to the reactants or chemical constituents which we use and get beautiful, equations. We have to attach numbers. Once we attach numbers, then we come to grams, kilograms, tons, kilotons, and things like that. Then engineering will take care of it. Plus, side by side, applications of those things should be also promoted so that you get the processes far useful and better human life. This is what I would like to conclude from this talk. And I got so much fascinated by these 2-dimensional materials. I have written 5 books on it and published something like, 20 papers, basic fundamental papers in last 10 years. And actually the thing which was very close to my heart, that is semiconductor technology, I have almost missed it. I didn't go to look at it, because that is not going to make our life better. Rather, these things are going to make our life better. Yeah. No, I tell you, it is. I think that, I spent 35 years in developing semiconductor technology, and we produced space qualified devices. We are very happy. Nothing better than that.
Pilani, Siri
Pilani,
Pilani.
yeah. We produced on 6-inch silicon wafers. It was a batch process line going on continuously. And our devices were space qualified. We were making, these NEMS and NEMS sensors. For the first time in the country, we produced all those. They were tested, and running order is there still, that if Pilani can produce worth something like 2 crores a year, they will take it completely. So,
I wonder that this chemistry is known very well. Why there is no breakthrough in getting our breakthrough?
No, there are
Material.
breakthroughs which are kept secret by other countries, and they work and they know the solution. We don't know the solution. This is, this is a current situation. I mean, it has been the situation.
those who have something, they generally keep it secret. For,
They keep it secret. They
commercial.
won't advertise.
But they could sell hydrogen in Moscow.
No, they are not reached that level.
They don't reach that.
They are not reached that level. So all.
I
it's all-
remember 7 years ago, China had a graphene program. We didn't have it.
It's coming up with the very
But in Indian perspective, like as I mentioned, like there's so much of disconnect between.
there's a disconnect.
Very
There
much.
is no disconnect. There is
I tell you, I was supposed to work for YMCA, if I can digress for a couple of minutes.
Look, tell me, Dr. Mate, we are discussing in a small group. And we have very knowledgeable people there. Where are we going? I mean, what is the outcome of our conference? Is it only to close the discussion and no further?
Live transmit of that.
Or it is going to be, look, we are not the people, but there are concerned people in the government who are still, who have to take the decision. Can this reach them so that some program on a larger scale can be sanctioned?
Actually, government the problem here will be time नहीं है वो अपना event inauguration और ये सब करेगा.
Well, I was supposed to be in the morning. This, Direct, I was supposed to be representing Jamia Hamdard for Direct to tell that, another interesting things, if you allow me 2 minutes. What we did when I was there in Jamia Hamdard in 2005, I asked a very random question like that, out of the box. I called all my pharmacists and, biotechnologists and those people. I said, what are you doing? They said, I'm developing this drug, that drug, so here and there and all that. All right, good. Now, we have been having a very rich knowledge of these herbs for treating human ailments. Fine. Why can't we convert these herbs into nanoform? So we took simple turmeric. I said, take turmeric. There was a very good chemist. He immediately converted the turmeric into nanoturmeric, which was water soluble. And it was injected to animal trial, for treating liver cirrhosis. To my astonishment, I am an electronic engineer. I really didn't believe it, that liver cirrhosis was completely cured and reversed. We have a patent on it. This we did in 2006. Encouraged by that, we took about a dozen herbs and converted them all into nanoforms. And they're all published and they're all patented, but because of some political reasons and things like that, we cannot produce medicines out of that. Now, second thing which I'm trying, now look at this. I have not left it. I didn't leave hope. I have converted today those nanoparticles into targeted drug delivery formulations that you can treat cancer by targeting cancer drugs on those herbal molecules and take them to the place where you want at the tumor. Not only that, this week we have introduced another new structure of carbon, which is a phosphorescent material. And when it will be attached to the drug, it will go on telling you where it is moving in the body, in the whole physiology. So we are trying to bring traditional medicine of Unani, Ayurveda, and Siddha at a level with molecular medicine, where all the targeting and imaging, all the technologies are available. So we can avail all those things and tell that, look, this is where your haldi can treat cancer better than your paclitaxel and all those molecules, which are very complicated names, and people are making money out of that. So
treat, not manage.
Yeah.
It's only the manage.
Yeah. So what I want to say is that the ideas are ample, but if government doesn't extend support, then these things cannot be brought to a fruition and cannot be brought to a common man level. I read a report by this WHO. There are 20 neglected tropical diseases. They have listed them, like leprosy and leishmaniasis, and there are a number of them. Unfortunately, most of the diseases are there in the developing countries, where they don't have money to buy drugs. So no company is developing drugs for them to treat those ailments. Now, WHO has floated a tender that you can take any amount of money and prepare medicines for those diseases which are troubling these developing countries on a very large scale. Hey, it is there. And let me tell you, people call Bhasma. What is Bhasma? Bhasma is a two-dimensional material. It is not oxide. Sorry. Because most of the metal oxides are two-dimensional materials. This has been misnomer. This has been completely neglected. And there is a whole, a lot of chemistry and physics is studied by people of metal oxide, two-dimensional materials. They can do miraculous things. Those who say that, your drug contains metal and it is toxic, actually it's a politics. It is not, it is not toxicity. It is a politics. They don't want. So there are a number of things I think we can handle, provided our younger generation is ready to handle these things and take it further. What we can do is we can advise. What we can do, we can advise, looking at the basics, and let me assure you that if we go in a right manner, we can work on the problems 15, 20 years ahead of what others are doing secretly in their laboratories. And it should be engineering problem, engineering solutions, and technology. Take basic physics, chemistry, and develop it. Don't go for fancy things. Don't go for complicated things, because nature has provided cures. Nature has provided solutions with a very simple algorithm. Why can't we do? Why do we make unnecessarily complicated?
Thank you.
So I think if my message goes, little further, I'll be very happy and I will be really rewarded.
अच्छा ये लोग ट्रेनिंग दे रहे हैं ISV full form is
My name is Saqib. I'm from Indian Energy Skill Development Private Limited. I'm a mechanical engineer from Madras and I'm a MBA in petroleum from Dehradun. I'm working for ISD as a business development executive. So I like to share some points on hydrogen. So hydrogen is actually a very evolving subject.
so you are in Delhi
Yeah, in Noida sector
अच्छा,
125.
but you didn't come yesterday, you came today only.
Yeah, I came today.
So what's your name?
My name is Saqib.
Saket, yeah. Told.
So hydrogen is actually a very evolving subject, continuously changing from last one decade. And what we have achieved from last 2020 to 2022, more than 50 projects in India has started. Reliance is working, IOCL is working, GAIL is working. And how last year we used to transport gases, natural gas via pipeline. Every city in India is getting connected via CGD network, city gas distribution. Now Reliance is trying to transport hydrogen blending with the natural gas. So up to 18% or up to 15% blending is also possible. So city to city hydrogen transportation is also viable. Pilot projects are already tested and everything is going on. So I have an example, like similarly how NASA alone was not able to build the space station in 1960s. He was trying, Russia is also trying. So alone Russia was not able to build and NASA was not able to build. So after a collaboration, a space station mission was successful. So similarly, every country in the world should go hand in hand together. A continuous collaboration is required to go for a hydrogen mission successful in India and abroad. For example, which countries are right now on a successful hydrogen economy are Netherlands, some countries in Russia. They are already running on hydrogen buses. Their homes are running with hydrogen heat energy. Their ecosystem is developed on hydrogen.
China has maximum.
China is producing. China and Russia are in a very large competition to produce hydrogen. So Russia, China, Europe is also producing hydrogen, and China is also producing hydrogen. So China is this rivalry actually will bring the cost effective of hydrogen in next one decade. This rivalry.
Okay.
So actually, I have also a point to discuss. We are producing hydrogen. For 1 kg production of hydrogen, we actually required 40 kilowatt of electricity to 56 kilowatt of electricity. And for a law of conservation of mass, after the hydrogen production, we used to get electricity from hydrogen breakup also. So after that breakup, we get only 36 kilowatt of electricity. Actually, we are getting less. But why we are doing this? Because hydrogen has a good transportation and storage option. Like we produce renewable electricity. Renewable electricity has some disadvantages, like its transportation is weak, its storage is weak. You need a lot of batteries to store. You can't transport renewable electricity from Rajasthan to Bihar. You first
It cannot be
dispatchable. First, you need to store, because renewable energy is very fluctuating. It is a time dependent, weather dependent, and you have to first store it and then you have to transport it. But in the case of hydrogen, suppose if a state or country is producing continuously hydrogen and they have stored it on a large basis, so it requires type 4 cylinder, type 3 cylinders, that is carbon fiber based cylinders, and you can store it for next 10 years, 20 years. And after that also, you can also create electricity. But in the case of renewable, it is not the similar.
So
you can
are
produce
planning a certificate course also.
Yes.
Okay. Your institution will be doing in-house, or you will be calling people from outside?
Actually, we have a team of program directors from other organizations, like we have former ED from BPCL, former ED from IOCL, Vice Chancellor from Indian Institute of Petroleum, and Vice Chancellor from University of Petroleum and Energy Studies.
Professor Chopra, you mean to say Vice Chancellor?
No,
Dr. Chopra.
no, he is retired actually. So his name is Shrikant Nanoti,
Okay.
Dr. Shrikant Nanoti.
Okay.
So they have collaborated together to form the venture for this hydrogen certification to create awareness among all the energy industry.
I think that may be of interest. Yeah.
So
Okay.
now, suppose in a year, if we are producing electricity, 1 megawatt of electricity is consumption for my personal use. So in the summertime, I used to consume more electricity. In winters, I used to consume less electricity. So during winters also, that hydrogen production can be similar in both the seasons.
Thank you. Thank you. Okay.
Different vast uses हैं,
Okay.
converting back to electricity.
Okay. Thank you, everyone.
Thank you so much. So we break for lunch and we have to come back by 2:15, just half an hour. Maybe 2:20, is it okay? Because we have to cover up for the remaining sessions. आपका सेशन आप जितना कहेंगे उतने बजे हम आ जाएंगे.
We will have a presentation by Dr. V.A. Mende. He is Senior Principal Scientist, Head Shale Gas and Non-Conventional Gases, CSIR, Central Institute of Mining and Fuel Research Institute, Dhanbad. He is the would-be director of this institute. Very soon. This is what I gather that information, and we wish you good luck. The lecture of Mr. Mende is Scope and Potential of CVM to Hydrogen Production in India. Any other introduction you want to make for him? I don't have the details. I think it's good if you.
Can I see 1 minute, Dr. Chavan?
Yeah. In this, it is there. Page 22. It's good to introduce the speaker, is not? You must know something about him. So Dr. Mende was born on 16th May 73 in MP, State of India. He has obtained PhD in Applied Geology on the topic Geologic and Petrographic Controls on the Coal Bed Methane from the coal seams of the northern part of the Cambay Basin, Gujarat, from the Indian School of Mines, Dhanbad in 2008. He has 26 years of experience as a research scientist, field geologist in applied and basics of the coal bed methane, shale gas, coal geology, and organic petrology. Dr. Mende has done extensive studies on Indian coal, lignite, and shale deposits of reservoir characterization, gasification, and other utilities. Dr. Mende has vast experience in coal and shale exploration, mining geology, gas potentialities, maturity analysis, absorption studies, reserve estimation, porosity, permeability, flow mechanism, production development technologies, reservoir simulation and modeling, GHG emission, inventories, and Indian coal mining and oil and gas system, coal mine methane, potentialities and feasibility, coal mine safety, underground coal gasification, geologic CO2 sequestration potentiality, estimation, absorption induced strain of the coal shale and advanced recovery of the methane, climate change, etc. Dr. Mende is the project leader of the National Shale Gas Project, funded by the Ministry of the Coal India, Advanced Recovery of CBM and Shale Gas, funded by CSIR. Also, lead of the National Shale Gas Mission Project and Shale Gas Committee in India. Dr. Mende has completed about 155 R&D projects sponsored by government, public, and private. He is a very renowned and scientist, done so much of work about the Indian coal, this thing. Since I come from the power sector, we have so much of complaints from the coal people. The quality of coal is not good. The Coal India is not following the mining principles of coal, and they end up in mixing the overburden and shales. He specialized in the shales, etc. Shales, stones, and all non-coaly matter mix up. We found now the situation is a little bit improved. Even the shovel tools, etc., the broken parts of the mining machinery were also found in coal. I studied the borehole studies of the coal. Our coal is not that bad, which is it is made to be when it is mined and supplied to the power stations. Your borehole studies are very good. However, the efforts are on, and today we are finding coal shortage. The power stations are not able to get the full quantity of coal, and there are problems. And the government has directed the various states to import coal, to have at least 10% mixing with the coal, Indian coal, so that the power shortage is not there. So that import of coal is in process, is being done. So we would listen to you on the coal bed methane. You have specialized, and tell us where are we actually on this project, and when can we get? My every time question is commercially viable project on coal bed methane. When do we expect this to be?
Actually, already started commercial exploration.
Yeah.
And that I will discuss later.
You can start your presentation and then
Thank
questions.
you, Professor.
We'll take the questions later on. Yeah.
Should I start?
Yeah.
Thank you, Professor Verma, sir, for the detailed introduction. Good afternoon, everyone. Today I have with me my young energetic researchers, the researcher.
Mic is not working. Maybe you can come closer to this.
Sorry, actually there is a slow. So I should, yeah. Okay, thank you. So with us today, me, my scientist colleague, Dr. Prakash Chavan, who will just talk after me on gasification. And the energetic researchers, I have with me Dr. Molika, then the Shashank Pandey, the Priyanka Shukla, the Vinal Vinod is, of course, my son. He is working. He is doing BTech in petroleum engineering, and also working on the CBM and shale gas. We are also doing the Moni Pandey, who is from the Jibaji University, and she is also working on the looking forward to work on the hydrogen technology in future. So before I start, my special thanks to the Dr. Maltiwell ma'am. I am associated with her since more than I think 2 decades. The first we met somewhere in 2000 in New Delhi itself, and we also made a foreign trip in Norway in 2003. There, the first I have represented the how much the CO2 sequestration potential we have geologic formation. And ma'am was in the DST, she was representing government of India for the CCS activities and the views in India. So my topic today, which I'm going to brief and discuss, that is the scope and potential of coal-bed methane to hydrogen production in India. There was a concept that in India, the CBM is not going to be that scale, what we were expecting. Yes, that, but there are the different limitations, different policy matter, different constraints. Even we have a central policy different, we have a state policy different. So all with the operators and everybody, being a researcher, we were also fighting how to get it the successful. And finally, that has been done because the first primary aspect was to find out the potential sites. So potential sites already that has been located, and then the block also awarded. Major constraint was the who will be going to use that gas. And the unfortunate part was just this slide will I want to show you in the eastern part. In the eastern part, we don't used to have a national grid gas pipeline. So utilization of the methane, and production is okay, but who will be going to utilize this methane? That was a major part, because CBM can be produced only for the 20 to 25 years, not more than from the particular block. Nobody was there interested there, the whatever the power stations or the existing industries are there, to switch out to the methane, the clean methane. So that was a major problem. But finally, last year, 31st March, that problem overcome. We have now the national grid of 3376 kilometers in the eastern part, from the Jagdishpur to the Dhanbad, via Dhanbad, from the UP, MP, Chhattisgarh, and then it's covering all over the potential CBM blocks in India. So this is done, and now this gas pipeline is the custodian is the GAIL, Gas Authority of India Limited. This has happened now. The pressure which is expected to the normal flow of gas in the pipeline, that is about 60 psi, 50 to 60 psi. But the present pressure is only 18 to 20 psi. So now everybody is, the CBM operators like ONGC, then the SR, then the Reliance, then the GCL. So everybody is trying to get rid of how to increase the production of the coal-bed methane. But in coal-bed methane, the most unfortunate part is we have a gas at very low pressure. The permeability is low, the porosity is low, but the block which we have targeted for the first initial production, all are the mostly saturated blocks. There, when you pump the water, you are getting the gas, and one well can produce the 3 to 5,000 cubic meter of gas per day in normal condition. But if you put extra efforts, then you can go up to 10,000 or more than that. And if you go pad system, now we have introduced a one pad system. There you can drill up more 5 to 6 wells in a pad, because we have a problem of the getting land in the Chhattisgarh or the Jharkhand or the West Bengal state. So the PAS system is very useful, There you can drill a one vertical hole and few the incline holes, and you can go up to that to 2000 meters in a subsurface and drain a maximum area. So that way you can reduce the land acquisition problem. And from one pad it is targeted, and some of the pad already started producing the gas. At 1 lakh cubic meter of gas you can produce from the particular pad. Now, what I'm going to add through this presentation is, everybody is talking about the different, and it is well known that now, yes, since yesterday, that the hydrogen is a near future energy. Yes, that is true, and it will contribute significantly in near future, before by 2030 or 2032. And there are various sources, and we know that more than 95% of the whatever hydrogen we required, that comes from the steam methane reforming of natural gas. Here in case of CBM, we have more than 98% of methane, and it's 1 to 2% of ethane, and 0.5 to 1% of moisture. So moisture easily we reduce at a pad site itself through the filters. This methane, because of the low production rate of a well, the operators always think, because ONGC in conventional wells, they always produce more than 25 cubic meter of gas from a one well. But here they say, oh, 3,000 to 5,000 or 10,000 is nothing. But the important thing is the CBM well can work for a longer period, more than 20 to 25 years. Hardly we have conventional well life 5 to 6 years. So that longer period without any down processing, because mostly we have methane, so there is no need of any downstream processing, and that gives a better economics, but for the longer period. Even in any CBM block, if you produce the conventional vertical well, that takes 5 to 6 years, whatever you have invested, that comes out in a 5 to 6 years. So industry don't want to stay for such a longer period for whatever they have invested. So now the hydrogen concept has come. So I am introducing, and I have already proposed the project in our CSIR, and ONGC and operators also shown the interest. So we are going to take up a pilot scale commercial demo project in one or two CBM blocks. There we are going to have this methane thermal reforming, steam thermal reforming, and formation of hydrogen. Whatever that CO2 will be generated, that CO2 we will be re-inject in a reservoir, because this is well-established process. When you in conventional oil and gas reservoir, and that is also applicable in the coal bed methane. When you inject a coal in a coal bed methane, that has a more affinity with your coal, and it absorbs in your coal internal pore surfaces, and it displaces your methane. So that way you can enhance your recovery, because through the conventional process, you hardly going to produce 30 to 40% of methane, the reservoir, the methane which is present in the reservoir. Rest of the 40 to 60% gas is remain there. So out of that 20% you cannot produce, because that 20% is held up in a very micro closed pores, that anyhow you cannot be taking it out. So rest 40%, if you inject, that you can take it out through the CO2 injection. That story, because why I told you, in 2003, first estimation was made for the geologic sequestration of CO2, and yesterday the previous speaker, the Gauri Johar madam, she clearly mentioned the industry only work after wherever they get the money. So this concept is very useful, because it has a multiple. It's okay. It's a integrated hybrid system, but it has a multiple options to get the money through the because the hydrogen has a more price compared to the CH4. The hydrogen has a more calorific value compared to CH4. And whatever CO2 comes out, that when you re-inject the reservoir, another 40 to 50% of CH4 you can recover. So this project, anyhow, we are going to have in very near future. So this is just a background I have told. Rest of the thing that the hydrogen, the demand, and the global how the global fuel cell, the demand is increasing. Everybody, since yesterday we are discussing. So these things I will not discuss. But anyhow, the things are we have to work on the hydrogen production. This also.
Coal can it be converted to hydrogen?
Yeah, it can be converted, but that's again the economics. Again the economics. Prakash Chauhan will tell that one. Okay, actually he is a master of the gasification. He developed the indigenous technology for the gasification gasifier, and we have a very large pilot scale project at CSR in Badanpur.
But when gasifier project at BSU 60,
Yeah.
it did not succeed.
Actually, that was a major problem of the high ash coal which we use for the gasification. So that problem we have overcome. He will discuss in detail. I can tell, but let him tell.
Okay.
Okay. So this is already well known why we categorize the hydrogen labels in the different types. That all because of the emission they made.
Okay, how much time you take? We have to manage
another 10 minutes. I will take.
Okay.
Okay.
And then some questions you take.
Yeah, please.
Okay.
So this is the published data that is available on the net. That in 4 rounds, 32 blocks already been awarded.
You're preparing for the questions?
Very important question.
Okay, so so the potential sites, the category 1 we have categorized, that is Raniganj, Bokaro, Charia, then North Kanpura, Swagpur. So they are the most potential block in India, and definitely at present they are contributing 3 million cubic meter of gas per day. That is 3 to 4% of our natural gas demand. But we are expecting by 25-27, because now the drilling is in every block, the operators are drilling day-night the production wells, and we are expecting by 25 to 27 there will be another thousands of wells for the CBM production. At present we have 1,050 CBM producing wells in 6-7 blocks, but it will be going to increase by 2-3 years. Yeah. In this mostly in the eastern part, including SR, GCL, ONGC. Yeah.
And what do you do to this gas?
They are feeding to the gas pipeline. They are feeding to gas pipeline at presently. GAIL. So this is the table just indicating that each operator how much well they have drilled. That presently how much they are. It's the latest data. How much they are producing from their blocks. So about 1,050 wells are under production, and 3 million cubic meter gas we are producing. So our expectation when we have started the CBM business, that was that we will be producing 9 to 12 million cubic meter of gas, but that is yet to happen because of lot of constraints which I told. This is already the different technologies which we use for the hydrogen production. But for CBM, because of course that these technologies are of course the economy driven, the most suitable technology for the CBM that I will only tell how this project we want to work on. That is there are the CBM wells, and from CBM well it goes to the compressor. The compressor is there where the gas gets gathered, and then it goes to the at presently it goes to the GAIL pipeline. But the part of we are not trying to convert all these CBM gas to the hydrogen gas, but part of the CBM produced gas can be gone through this steam CBM reforming process, and the operators can make money out of that, and we can get a clean energy. And also that CO2 capture, here CO2, because we have a very concentrated CO2 here, and we can make it more concentrated. Because yesterday also, why we are not capturing the CO2? The major problem with CO2 is the concentration, and second is the economics. So with capturing, nobody will do unless and until they get the money. But here capturing is very useful. When you capture CO2, you can inject in your reservoir and you can produce the gas. So steam CBM reforming is the suggested process, where at the site itself there will be the pilot scale demonstration, and this will be the chemical process where the CH4 will be steam through the steam, it will be reformed into the hydrogen. And just for the sake of the completion, I will tell you, because there are a lot of questions in the forum. You are sequestering CO2 in a coal seam, but in future, what will be happening with that CO2? Because CO2, whenever you inject in a reservoir, it should not be in a gaseous phase. It should be in a critical. It should be in a mobile phase. So mobile phase, why? Because CO2 has a very strong affinity with your reservoir. When you inject in a well, it gets absorbed in a surrounding influence area of your well, and because of that, it will not pass through, or it will not percolate for a longer distance. So that is the major issue with the CBM. That's why with the CO2 in a reservoir. That's why everyone suggests wherever we have a deep coal, and in CBM mostly we are dealing with the deep coal seams. So wherever we have the coal seams more than 800 meters, there, because the CO2 critical pressure is 80 kg, so normally that pressure we get at a depth of 800 meter. There when you inject the CO2, it will just dissolve in a aquifer water, and it pass through the reservoir, and slowly it get absorbed in a pore system of the reservoir, and it displaces the CH4 molecule.
The source of CO2?
Here the thermal dissociation, whatever gas we are producing, methane, the same methane we are thermally means steam reforming process will be there. So we will break it in the form of hydrogen and CO2, and that CO2 we will inject in a reservoir.
And the coal, do you mine that coal also?
Yes, that's I'm going to tell you how it will be done. So usually coal has a two kind of pore system. The flow mechanism system. One is the micro or the pore system that we call the max, and another is your cleat and fracture system through which the gas passes. So we tell that is that coal or shale has a dual porosity system. And the ECBM experimentation already been done in the US, Canada, and Japan. And they have finally concluded and summarized that the 77 to 95% in US, and then in Canada and Japan, that 95% of methane present in a coal can be recovered through the CO2 injection. So this is already the trial is done. And commercially, few in Alabama and the other basins of US and Australia, they have already started injecting CO2. One story I will tell you, and some of the people may be knowing, madam may be also knowing. In Balul, ONGC tried CO2 injection in one of the oil and gas well, and finally they concluded that yes, CO2 can enhance the oil and gas recovery. It's a well established and well tried technology. Yes, but the problem was when they actually wanted to do it on a larger scale, they faced the CO2 problem because CO2 availability was not there. So finally, they have not continued it. So talking about lot. Yes, sir. Yeah.
So those areas we have done thermal and recovery has happened.
Yes. Yeah.
And the same technology we only see carrying also.
Yeah.
Same.
Yeah.
That's it.
Yeah. So major problem is the CO2 capturing. So here the scope is there that CO2 you can capture during the thermal reforming of the CH4. And the experiment, the trial they have done, it shows clearly that the below blue line is the normal curve of the production. But when they have injected that pink line after a period of 30 years of CBM production, and suddenly the whatever gas they were producing from the well, that the amount was doubled. So suppose they are producing the 5,000 cubic meter, and it was complete the 9,000 cubic meter per day. So this happens when you inject the CO2 in a coal seam.
So
CO2
CO2 get fixed up when you extract.
Yes, I'm coming to that. I'm coming to that part. So just simply saying that we are going to inject CO2 in a coal seam, it's not that easy task. When you inject the CO2, it will swell your coal. And anyhow, anyhow, you have a very low permeability in coal. Unfortunate part is we have hardly 3 to 4 millidarcy. But for any normal production, you need a 10 to 20 millidarcy of your permeability. But the good part is we have the advanced technologies now. You can hydrofrac your well in vertically or in a laterally or even in a horizontal wells. You can multi-frac. So that technology with us in the past, the one of the UNDP project we have developed, and we have that indigenous and our own capacity built it in that project. So that setup is with ONGC. Now ONGC is doing that. So that is handled. But when you inject the CO2 in a reservoir, what happens? Your coal gets swell. And because of this swelling, the swelling of the pore matrix system, the whatever permeability and porosity you have, that get lost. And because of that, the production which you are expecting, that is getting low. So, so what we have done in the laboratory, we have developed a setup, and there we have injected the CO2. We measured how much coal gets swelled at very micro level, and to control that. So what we have done, we have added a nitrogen in a different mixtures, say 85% of your CO2 and 15% of nitrogen, and then we found that swelling got stopped. So whatever permeability that was there, that is remained there. So that way you can optimize, and accordingly we have remodeled, we have corrected the permeability, and we have developed a model for permeability, how the permeability should be for the optimum production from the well. And now coming to your question, once you recover the gas, after that injection is hardly for the 3 to 5 years. After that, there will be no gas in your reservoir. So in that case, the CO2 that is there in the reservoir, that should be mineralized. So we are developing a kinetic process that Priyanka Shukla and one another fellow, he is not here. So they are developing a mineralization kinetics. Your coal and shale has a active cation anion. In subsurface rocks, they have active cation anion. They react with the CO2. CO2 as an acidic material, so it reacts with the CO2. We are also trying to add few of the naturally available minerals. Naturally available minerals like the dolomite, the magnesite, the iron ore. Can they work as a catalyst? That is under experimentation. I am not sure what will happen, and what pH, what condition we have to maintain, what temperature, pressure we have to maintain, so that mobile phase CO2 should not remain there. It should be mineralized in the form of sodium carbonate, potassium carbonate, aluminum carbonate in the solid form. So that is going to happen, and by the end of this year, we are expecting that kinetics will be established. So once it is done, then we will be injecting CO2 in a reservoir. After complete recovery, it will be mineralized. And even after you go for any kind of mining or any kind of process there in that particular block, there will not be any CO2 leakage or CO2 hazards.
But in the beginning, you said coal bed methane can come up for 20 years. Now you are saying after 5 years we'll do it.
Actually, that is the problem. That most of the coal seams, in the category 1 are near saturated or saturated. But in the second blocks which we are going to have, they are hardly 50 to 60% saturated. So they will produce only 5 to 6%, 6 years of gas. Here also, because we have started commercial CBM production in 2007.
Now, have you
So
made,
already 15 to 16 years is over.
Dr. Manjay,
So, yeah.
have you made any estimates or targets of production of CBM so that one can plan something? You
Yes.
see, we have been, did not have a good impression when ONGC or GAIL or
Yes,
all
yes.
these together gave us an estimate and we put the gas-fired power stations. And the gas was not supplied.
Oh.
To some of us, they said that you take it on fallback basis.
Oh.
So we can't build a power station on fallback basis.
Oh.
So these have been the problems, and even today our gas-fired stations are not working. Practically not working.
Yes.
So that investment has gone waste.
That's why now
So this project which you are taking up,
Oh.
is it only a kind of a laboratory research project that you are trying to generate
No,
CBM?
it's not laboratory.
Or do you have a target long-term basis so that one can plan for consumption of this gas?
Yes, it is there. You see, this is just, I am talking about the CBM, but parallelly shale gas is also coming. Shale will also give the gas another.
No, I'm talking
15
of any
years.
targets. It is coming here and there is one thing. But there has to be an informed target that these are our, every department has a target. Coal has a target of production. It may fall short sometimes. So do you have you fixed up such targets so that this helps in planning of the sector? So any such thing has been
Actually,
done
the
or not?
answer is national grid. Actually, the national grid. The national grid which we have, the CBM we produce for 20 to 25 years. After that, that national grid will have another option. Because gas, if anybody,
we have a target for CBM production year-wise. So that
year-wise we are expecting. Not exactly thermal power, we can have another options also. There are a number of other options. Actually, that was the problem.
When we allocate coal mines to some people, that an estimate is made how much coal it has, how much it will survive for 25 years, so what capacity of power station it will sustain. That kind of planning has to be done.
That's what CBM based power stations are not suggested. Nobody switch over from thermal power to coal power. So gas based. We have gas based. That I know.
the only company is actually making good profit from CPM, yes. And it is in Naniganj. Even RIL, I don't think producing too much.
No, actually, there was there was a problem of utilization.
The long-term plan or mid-term plan, all that has not really come up of CPM.
Yeah, that's right.
It's still more in the R&D, a bit commercial.
It is something like that. Yeah, right.
Not exactly the R&D. Already it is in a very it took a speed. SR is producing, GCL is producing, ONGC also started.
It's not even SR, etc. It's not. They're not, because they have so many resources, separate resources. So they're able to absorb this somewhere here and there. They have the power stations and the gas-fired power stations.
Initially, the problem was the utilization, but the Max and the SR both have installed one fertilizer plant in Panagarh, Raniganj. Yes, and their per day requirement is 60 lakh cubic meter. Means 6 million they want, but presently they are only getting 30 30 million, 3 million. So that requirement.
Any
is not-
targets for hydrogen production?
Not at present.
So this is the problem which we face in our country. For example, there was a lot of noise about coal gasification, and we tried a lot. NTPC sent a huge amount of coal to US, and finally the result was that our coal cannot be gasified, and IGCC
Actually, the
cannot be
problem
done.
is, sir, problem.
One
just-
small
just- I
plant
will- I
was
will- I will
done
just add. Actually, the problem
Huh?
is.
That's an old story.
No, actually, the problem
No, old
is
story, but new
always
story
we
has not
compare
come up, no, that
Indian
is the
coal,
problem.
Indian basin, Indian shell with the US. That should not be
Power sector
done.
will not come up with the gasification plant.
Do we have for high ash coal technology?
Yeah.
BHEL has done this.
Yes, he will tell. He will tell what we have done.
This has been going on, going on. I remember in 1990, one
This lecture we will discuss CBM.
ex-secretary of Ministry of Power, he wrote me a letter that if you succeed in 1 megawatt coal gasification plant, I will be very, very happy.
Right.
Just wrote, he came to know. And
When
he
it
wrote
was,
to me.
when it was, madam?
Yeah?
When it was?
About 1990.
At that time,
Maybe early 90s.
a small plant was put up at BHL Trichy.
Actually,
I have seen that.
Yeah, you have seen that, okay.
That was a different thing. But coal gasification is that if you can put up one power plant of 1 megawatt, I'll be very gasifier, coal gasifier. So I'll be very happy. Not plant, but gasifier of 1 megawatt. And I really tried my best for so many years after that. But I did not succeed
Ma'am, now you
because
will-
power sector will not budge.
now you will be very surprised that the technology which we have indigenously developed, that is the latest one, and we have resolved most of the issues.
Okay.
Now it is, the government has given 100 million ton target.
Yeah, yeah.
Okay, any other questions people have? Hello?
I have one question.
Yeah. Can you use the mic? Can you use the mic? Mic is there, okay. That one, the portable mic. नीचे नीचे इसका कुछ प्लग है.
My question is, you see the Raniganj coal mine, they are basically thermogenic.
Everywhere we have thermogenic.
But
In Godwana, everywhere we have thermogenic.
Coal-based methane, they can be thermogenic or battery, both are possible. Okay.
Oh.
Now thermogenic obviously has a higher calorific value. Okay. Now the issue is that means basically there is shale. That shale is generating the gas essentially, and they're getting trapped in the coal.
No. Coal is generating the gas. Shale is also generating, both the generating gas.
Main,
Wherever is the organic matter,
yes,
it generates.
yes, no. I'll tell you all about the history about it. I'm an oil and gas man. The point that is important is, if you talk about coal-based methane, right there at 100 to 1200 meters, you may not have a generation. The maturation, the maximum maturation of hydrocarbons.
Where? At what depth?
Will come out at a slightly deeper depth. So most likely, just listen to me for a minute. See, you listen to me for a minute. Most likely, there would be shale gas, should be possibility of a shale gas is much more there in places like Raniganj.
We have shale gas in Raniganj.
Yeah, we have
Yes,
a
yes.
possibility of shale gas.
Recently, I have completed one.
My question is, instead of going for coal based, and if you can explore shale gas, then the value would be much more than coal based.
Sir,
So
sir.
why aren't we going into that compared to coal based?
Sir, the thing is in 2017, now that CBM shale gas policy is modified, and the operators now free to go for the CBM and shale gas both. Because when you drill a well to intersect the coal seam, in between shale also come. Okay, and just for the, because you asked, it is not like that only the shale or coal is generating gas. Wherever you have the organic matter, it generates gas. Okay. I will give you the letter.
Okay, it's okay.
Okay. Second.
Any questions from the younger people? Have you understood what we are discussing? Raise your hands.
Yes.
You understood? Okay, good. How about on this side, Professor?
It is okay. I have interrupted him.
No, the people behind him. They were busy in something. Okay. So,
Should I have enough?
yeah, that's okay. Malti, you are writing some questions. You're not asking.
No, no, it's okay. What I was just trying to say that I really made it a mission because if somebody says to you, then you feel committed that you have to do it.
Yeah.
And but I found that it could not be done for various reasons.
Right.
Cost was one of them because of high ash coal.
Yeah.
And
Yes.
removal of impurities was creating a hell of problems. So it was not becoming possible despite many
Yeah.
sincere efforts by several organizations, and we really tried. And then it came carbon sequestration. So the focus went into, instead of that, went into CO2 sequestration.
Okay. All right. So next, thank you very much, Dr. Mehdi.
एक मिनट आइए.
Dr. Mehdi, some presentation, I suppose. We are grateful to Dr. Mehdi for come here in spite of his busy schedule.
Yes, yes.
Yes.
Thank you.
Now, Dr. Prakash. What?
No, Dr. Rakesh will be connecting.
Dr. Rakesh,
Yes.
you'll be connecting there.
No, virtually.
Virtual. Okay.
So we can tell them. बताओ. हाँ, उनको कहो connect कर. आ गए? He's come on the line.
He has come? All right. So we would invite Dr. Rakesh Kumar. He is a former director NEERI, OSD CSIR headquarters, New Delhi. We are grateful to Dr. Rakesh having agreed to join this conference on invitation of Dr. Malti. And this special address by Dr. Rakesh Kumar. And we know the contributions of NEERI in the past when the talk was CCS, carbon sequestration and storage. And there were several issues were raised in the past for adoption of CCS technology in our power stations. Cost was one of them. The disaster management is another issue. And there were several other efficiency of the processes were going down. And at that point of time, consciously, we did not adopt CCS technology, but NEERI, in their organizations, have done lots of research on this. And they did convert the carbon dioxide into a useful material, construction material, to be used in the construction area. And I do not know really what happened to that, whether on a commercial scale it was developed or not. If Dr. Rakesh Kumar touches upon that subject, is good. But now can we have Dr. Rakesh for your address? No. Thank you very much for joining us.
Thank you very much, Chairman sir. It's pleasure. And
can you be a little louder so that we can hear you properly?
Okay, I'll make the. Can you hear me now better?
Yes, yes.
Right. So thank you again, Chairman sir, and also Dr. Malti for inviting me. I'm extremely sorry that I couldn't make it. My desire was to be there in person, but due to some other medical emergency, I just couldn't travel to Delhi. I'm going to speak on certain topics which are related to CCS, but primarily also looking at how we are dealing with the climate change issue in India with respect to what people are talking about internationally. So just allow me to share my slides, and then we can go ahead. Just one second.
Yeah, okay. Who is his slides? Can we have?
Just
Yeah,
come.
okay.
Can you all see my slide? Oh,
Yes, we can see, yes.
okay. So the whole idea of looking at whether it's CCS or any kind of technology, whether in India or elsewhere, the issue was how are we dealing with that within the community of people who understand this subject. And I've tried to address in this whatever 20-30 minutes that I'll speak, what has IPCC brought in its report on summary for policymakers, because that is what is going to drive what we need to understand. So I'll talk about bit of background of climate forcing that we are talking about. And this there is a debate which is going on that while doing climate change mitigation efforts, we shouldn't be forgetting our pollution control. And is it something which goes hand in hand or not? In many cases, probably not. So India being a country where we have a challenge of pollution control as well, almost in every sector, whether it is air pollution, water, wastewater, hazardous waste, and climate, of course, gets added as we go ahead. And then how is the international drivers on climate change is making demand on us on an overall basis. So when we talk about climate forcing processes, I will not go into details. This is something which is all known to us. It is anthropogenic and natural both. And there are processes. Besides processes, we also have agents. Now in these climate forcing agents, we always get new and new elements which is getting added. We are talking about now short-lived climate forcing agent. Earlier we were only talking about carbon dioxide, methane, nitrous oxide, and some CFCs. But when we talk about some short-lived, we are talking about black carbon and related other molecules as well. Let's look at some numbers that that we need to worry about when we talk about how do we deal with it. And some numbers which have come in, which talks about we need about $1.4 trillion, which is the investment needed if India has to reach net zero by 2070. Government has done some kind of investment approval of about 1,500 crore, which is in only one particular place. And then when we talk about Ministry of Environment, on the other side, on the research aspect, we found that there is some reduction in the allocation which has happened. On the other side, if we just look at air pollution, and when I say air pollution, in pollution, we do not count CO2 and methane. So here we are talking about particulate matter, and we are talking about sulfur dioxide and related things. This itself will require India to spend about 10.7 lakh crore, and which will be almost equivalent to 5.4% of India's GDP annually. Now, when we talk about these in terms of global economic losses, they look smaller number, but for us, if we have to do for the climate change and air pollution together, we are talking about a bigger number, which probably we need to struggle and think, how do we address these money coming from? Where will it come? Who will give? So I'll just take you through some of the sectors. It's a very detailed thing, but small sectors that I think I should share with all of you. That what is the learning which is coming from Summary for Policymakers, which has been released by IPCC in the month of April. So if you look at demand side management primarily, not on the control side as such, but if we take industries emission, which is what we are discussing right now, we see that in the wordings which have been used, it says that it will entail coordinated action throughout the value chain for mitigation options. Now the problem is that we haven't yet defined within country as well as across many countries, are we going to do all of it for the whole supply chain or part of it, and what is that applicable area that we need to do and which way we will do. These are the kind of work that we need to do as a community of practitioners in India, which looks at these issues of demand management, energy materials efficiency, circular materials flows, combined with abatement technologies. And after that, we are talking about transformational changes in production processes. What we mean by transformational change in production processes is that before we produce something and we create CO2, can we do something beforehand so that that process itself does not generate anything at all? And that is where the issue of new and alternative production processes come in, which could be completely breaking the normal conventional routes. And when we want to do all of these, this is what the statement says, that how these can be applied will vary across regions and different materials. So when we talk about coal or metals or steel or cement, all of these will change from place to place, location to location. The other related important statements which have come in this policy is saying that action to reduce industry sector emission may change the intensity of greenhouse gases across value chain. And since it has high implications of trade and also the industrial atmosphere that we have in our country, this will require a complete understanding of reallocation in a distributional effects for employment and economic structure. Just to explain a little bit more, supposing we are changing our steel making processes, the cost of the steel and the people who are involved in it, if it changes from one place to another because of the cost and CO2 mitigation, we will have such serious social problems or social issues which we need to address as we go ahead. Similarly, when we look at policy packages which each country has to make, it states that it should be socially inclusive, phase out plans for emission intensive facility within the context of just transitions. Now, this definition across world has been debated a lot. Within our own country, when the statements were made that those people who are engaged in coal-related activities can go to renewables and it will be much more effective for them and they can be retrained. Do we believe that people who are in the sector of coal mining and related things can immediately shift to solar and wind? And can they not do the same thing in the same area, or do they have to move from one place to another within our own country? The second sector, which is a big cause of concern for we need to debate a lot, which is urban areas and planning related to that. So here, I would say there are some good wordings which have been used, which says the potential and sequencing of mitigation is to depend on the land use and spatial forms and developmental level. But definition and spirit of language changes. When we say FAR or floor area index that is used in our country, many other countries they use something else. So when we talk about doing something with established and older cities, we have to start looking at not only improving them but repurposing or retrofitting building stocks with low material, these are the keywords, and energy footprint. Now, when we have major cities with 60% and plus people living in substandard housing stocks that we have, what kind of retrofitting we can do and how do we do it so that we have low material and low energy use. Targeted infilling is a process where we start in the dense area wherever possible. If we can get more and more people to live, that is what we have to start thinking in terms of planning. Although world over people are talking about non-motorized and public transport, I think India will have to specifically think of our traditional non-motorized transport of cycling and public transport that we used to use. Most of our roads and the urban planning is actually making people to go back to take their two-wheelers or four-wheelers, and that is a reform which has to actually happen. And for all of these, we need finances and legal reforms in this case. Similarly, as we go ahead in urban areas planning, when we have rapidly growing cities, co-locating jobs and housing is going to be a major thing which is needed for a compact urban area that we are talking about. And when we look at all of these things together, for new and emerging cities, much more easier to do. But when we start doing it, as we have national building code in place in our country, we haven't yet started designing our urban forms on the basis of environmental services. They are still on the basis of how much land is there and how many buildings we can make. The real challenge is going to be in older cities where we have very archaic local rules and land rights and reforms related issues. Unless until that is done, all these large urban poor will not be able to accommodate, and they are the ones which they will need equity in energy, water, and space, all three together. Emerging cities, as I said, can possibly be taken care of much faster than anything else that we are thinking of. So these are some numbers. I'll not go into details, but it is what is important here is that in 2019 estimates, it was said that global direct and indirect emissions, when we talk about cement, steel in construction and related things, non-residential buildings had 55% increase when we take base level of 1990, and residential building about 50% increase. And that is where this whole material which is going into residential building or non-residential building per se, particularly cement, steel, and for producing these you need coal. All these energy related issues have to be integrated and counted. When we get into transport sector and on demand side, as I mentioned earlier, we are looking at reducing transport sector emission in developed countries and limit emission growth in developing countries. Now, these particularly in transport sector, these numbers are linked to 1.5-degree limit that everyone is talking about. And if we don't do following things, then we get into 2 degrees centigrade model scenario. So here we are saying for 1.5-degree scenario with for 50% case overshoot model scenario, global transport CO2 emission must reduce by 40 to 68% by 2050 when we compare with 2020. And these all will require a whole lot of effort to address transport sector, which is not easy to deal with. Even when we are adding electric vehicles, as long as electric vehicles are getting energy from fossil fuels, we are not actually doing anything good about it, because every time when we have energy transformation, we lose significant amount of energy. So only solution could be that we get into renewables more and more, and possibly use biofuels as we go ahead and move forward. Just to give you an example, some of these graphs is being shown and which has come from the main document, summary for policymakers. When we take sector of agriculture, forestry, and other land use, these are the numbers which are being given that these are the kind of actions that can be taken, and it will lead to reduction in CO2 values. Now, what happens in each of these sectors, agriculture, forestry, and land use, that we need to understand the barriers for implementation. It has very large potential for CO2 mitigation, but barrier to implementation is that we have competing demands on land. On one side, we need forests, and unfortunately, wherever we have forest, that is where we have all the minerals lying. So how do we deal with it? Conflict of food security and livelihoods, and then complexity of land ownership, particularly in our country, is a big barrier. Cultural aspect, I'll just leave it for time being, but those are actually equally important. So this is a very famous graph which is there in the summary for policy. What it actually shows, you may not be able to see the color very well. What it actually shows starting from this oranges color is that for all the technology and energy, building, transport, and others, $0 to $20 per ton of CO2 equivalent are the technology related things which is available. However, when we start mining this data, when we start looking at this data very carefully, what it actually shows, there's a large uncertainty in each of these categories. You see this? The largest potential is looking like from agriculture, forestry, and land use, but we have large uncertainty because as I showed you all the factors in the previous slide. The ones where we are putting a lot of effort is industry and transport. But if you see the potential, it's much lower. But what is important here is that each of these monetary cost has to be accounted for and looked at from the angle of not only the European calculation or developed countries calculation, what the cost of the technology is going to be. If somebody is already in the TRL 8 and 9 level, we know the cost is formed up, and we know what the cost is going to be. But if it is at TRL 1, 2, 3, we are still struggling. And that's an example of the previous speakers who was talking about using CO2 for extra gas or oil recovery. In this sector, I just blown up picture. If you see here, we are talking about reduced conversion of forest and other ecosystem, highest potential. But how do we do it? We have no idea. Ecosystem restoration, afforestation, reforestation, again, a significant possibility that happens. Carbon sequestration in agriculture. So these are the areas where all the research community has to sit together and make those mission projects, not only in terms of R&D, but also implementation. Fortunately, we have excellent team of people who are doing R&D, but we have a very poor team, and I'm sorry to say that, who can actually do that actual implementation in the field and showcase that actually it is possible to do it. Similarly, when you see building and transport these numbers, I would like to show something which was also of interest of today's discussion as well. When we talk about industry, although the potential seems to be comparatively lower than agriculture, forestry, but when we talk about energy efficiency, material efficiency, enhanced recycling, we see a lot of policy changes being done by the government, local government, as well as central government. When we talk about fuel switching, when we now talk about natural gas and bioenergy and hydrogen, we have a big challenge. And unless until we have the confidence of uh, dealing with each of these sources, whether it's hydrogen or bioenergy, the reliability factor, the safety factor, and the environmental related issues have to be dealt with at a very high confidence level. Then only it will get implemented. The feedstock decarbonization and process change is another area where we need to have more piloting happening at a higher scale, and then only we could possibly go ahead and do it. When we talk about carbon capture, utilization, and storage, all of these things together, CSR has initiated this Net Zero India Cluster of Excellence. There are various labs in CSR, starting from SIMFER, NERI, CBRI, IIP, ICT. There are many labs which work in this area to combine the strength and look at how do we bring our TRL levels up to 8, 9, so that actually things get done and get implemented. Otherwise, if we do not showcase all of these at scale, chances are that India would again be importing all of these ideas from elsewhere, and then so-called finance coming for climate-related mitigation will look like somebody is investing it in India and then taking money back. And the last one which you see here is the sector where which we can do much faster. Others may be a little more complex, but reducing methane from solid waste, technology is in place, extraction processes are in place, its utilization also is in place, but we are not implementing it. And that's only because urban local bodies, their reforms and their finances are not actually lined up or not actually done in a way that implementation can happen. That's why it is problem. And of course, same thing, emission from wastewater. So this is what is happening for the whole technology processes listed in the summary of policymakers on the left-hand side. It is important to remember that all of these which have been derived from developed countries' data appears to be cheaper, appears to be easy to do, but they are not all that cheap and easy because finances are the critical ones, and the scale at which technology has to be used and utilized is not in place. And therefore, technology transfer becomes very critical. A recent report of MIT Technology Review puts India somewhere in the middle. They call it Green Future Index. And I'm sorry, a lot of these indexes are not very reliable, but here I felt that there was a reasonable data and parameters which were used. What is important here is that India should not be slipping on the left-hand side. It should be trying to cross over, because in economics is called Kuznets curve. If we do not cross that, for everything else that we do, it will be more expensive per capita. But the moment we cross that barrier, the per capita cost of our transition is going to be much, much lower. So implication of all of these are some major points that I wanted to highlight here. Was overuse and high emission of developed countries can be reduced through technology transfer policies, and this policy messaging does not apply only to developing regions. This can happen within the developed countries as well. That's very, very essential. Industry and transport are very hard to abate because we have already done quite a lot of work. But if you want to do an international growth, we want to do import export related things, the money required for doing this requires high cost and technology transfer related issues to be addressed. As I said, agriculture, forestry, and land use has very high potential, but we have to start doing state by state, district by district, social and economic barriers study. And that's where from science and technology, one has to also come into social aspect and economic aspect for addressing our climate change needs as we go ahead by 2030, whatever commitment that Government of India has given. Cost of many of these options are on the basis of life cycle cost is not yet very well known. But what is important here is that locally we should start doing the benchmarking so that regional variation can be further reduced and uncertainty can be reduced. The new challenges which are emerging could completely be new things altogether. So when we talk about renewable energy, the renewable energy cost may have reduced, but grid integration cost has not yet been counted. Material mining, which is being done for the batteries, is not still in place. Material being imported for batteries to be in place. Still, we have geopolitical other issues besides the cost aspect of it is not in place. So we need to do all of these studies together, and then finally look at equity and climate justice both within and between countries. Otherwise, all these mitigation policies will be limited to only one single location, which may look lopsided and it will not yield the benefit that we're talking about. Why I'm saying that is because the window of real control is between now and 2030. Because if we don't do that, we will not be able to meet 1.5 degree limit that we are talking about. So this is my last slide. Particularly, I wanted to, as I said earlier, specific to India and developing countries, it is important to lead from the front, which has been seen in renewable energy sector. The R&D studies and global practices are actually required, and where that's the partnership with other people is extremely important. The debate of pollution and climate change is another angle which India should start, because India has been one of the leading country from developing world side, which has been able to put in a lot of effort to bring the rationality in the assembly for policymakers. So India must also not forget pollution control in this whole process of climate change. Otherwise, we would have a very lopsided growth as we go ahead in 2030 to 2050 period. Why I'm saying that again is that we have actually very limited carbon budget left to achieve net zero goal. And that's why it's essential that this debate is done much more strongly. So thank you very much for the time, and I'm sorry I couldn't make to the real in-person presentation over there. Thank you.
Thank you, Dr. Akesh Kumar, for telling us so many things, and you also raised some questions about environment and climate change. Let me put up some points for your. Let me update. I mean, in that respect, you raised an issue about the environment and pollution, emission of the particulate matter, sulfur dioxide, etc. We are very much aware, and our pollution standards have been revised, and they are better than the Western countries, including US, very strict. And government has allotted money for implementation of those, say FGD, etc. in the power plants. We are doing it. The target has been fixed. And so we are serious about it, number one. Number two, you raised the questions about our industries. The Bureau of Energy Efficiency is very serious, and they are interacting with industries and their emissions, etc. And the efficiency, particularly, is under control. And they are given the targets every year, and they are being monitored, and the implementation is being done. And you know that the star rating on the appliances have been done. When I was the DG of the Bureau of Energy Efficiency, I started this, and now it has gone to a much larger extent, and many more appliances have been covered, which are available in the market. They keep on revising the star rating also. As far as the renewable energy is concerned, and you raised an issue about the renewable energy, the government is very serious about it, and we know that the batteries are expensive. Therefore, the alternative methods are being thought of. The hydropower stations, especially the pump storage schemes, are being built seriously so that they could replace the batteries. We know batteries are very expensive, and if we have the batteries, the power cost goes to something like 15-20 rupees a unit, which we cannot afford. And government is seriously taking the of the pump storage hydro schemes, and these pump storage will be charged by renewable energy only. Because if we charge them by the regular coal-fired or some other stations, for example, then it doesn't become a renewable thing, and then it becomes very expensive also. So all these future pump storage schemes would be, the pumping shall be done by the renewable energy during the daytime when the sun is available. And so this is being thought. The now we have to be carbon neutral by 2070. The Prime Minister has given a target, and it is beyond our imagination that the coal-fired stations will not be there. But the 70% generation now comes from the coal-fired stations, and as per our some estimates, in 2070, this 70% may become 30%. At that point, the share of the thermal energy will become 30%. But this 30% will be, in absolute terms, will be more than the 70% now. And therefore, coal-fired stations would stay. And but then a lot of improvements are there on the coal-fired stations. We are adopting the ultra supercritical technologies, and the station sizes are going high. We have now commissioned 800 megawatt units in the country. They are quite efficient as compared to the older units, and many more actions are being taken on the, as far as the power sector is concerned. The transport sector, I think the transport minister is very serious about it, and the Niti Aayog has given an indication that on two-wheelers and three-wheelers, they will be electrified, and batteries will be there, of course. And but on four-wheelers, we are going a little slow because we are not very sure whether the hydrogen would be there or the batteries have to be there. We have to be very firm on this. And the serious attempts are being done on hydrogen. The various institutions are involved, and we are doing it. And so, therefore, I mean that the country as a whole is very alert to the situation. You said we must lead, and I think we are leading and taking. But then we are keeping our interests in view. To protect our interests, I think the Prime Minister has taken the right decision and saying that 2070, because the rural areas is still, we are not able to give them the electricity. And there are many suggestions that the solar electricity can be there in the rural area. But the question remains about the night time when the sun is not there, batteries are expensive. So with these remarks, I think, would you take up some few more questions from the audience here, if there are?
Yeah, I'm okay with it, and I welcome all the comments that you made. Absolutely right on the dot. So I can take few questions if there are any, and I'll be happy to respond.
Dr. Sen, you would like to say something? Any participant? You have any questions? You have? Yes. Okay. Introduce yourself first.
Myself, Vandana. I teach in Motilal Nehru College, University of Delhi. So you were talking about, you have very nicely given an overview of IPCC report. And you have given this idea, or actually I would say the IPCC have given the idea that agricultural, forestry and land use have a lot of capacity for the transition towards reducing the emissions on climate change. So what is your take on nature-based solutions? So especially in Indian context, do India have a scope of imposing, or I would say, utilizing nature-based solutions to reduce the emissions to a certain level? I'm not saying that nature-based solutions can achieve net zero target. Only nature-based solutions can achieve net zero target, but do they have any scope in India? Because in other countries now we are, now we are focusing towards more of nature-based solutions. But what's your take on Indian context?
Yeah, so very rightly said, nature-based solution is what is being propagated, and it actually sounds right and absolutely true, absolutely no problem. But when it comes to inter-country comparison, most of these countries who have lower population and per capita, their green areas and the forestry is much higher than ours. They will be able to do a better negotiation with us later on. 5 years from now, 10 years from now. So while we do this, so let me just finish it. We must do what is to be done for nature-based solution. We must address that internally much more strongly. But at international level, we must not be negotiating that we will make it as part of our rule or regulations. Because the moment you do a rule regulation based nature-based solution, the poorest of poor in a country like ours, Brazil, they will suffer, because there'll be limitation that you cannot use this and you cannot use that. So NBS as a concept is absolutely right, wonderful thing to do. But as I mentioned, internationally we have to be very careful when we agree on certain terms and conditions there.
Okay, but we do have scope for NBS in India? Yes. And especially in context to what I believe, like India as a country, we have a lot of traditional knowledge that we use it presently also. Like for example, forestation or afforestation, and we have ponds, we have wetlands, and we have sacred groves. These are the things that are included in NBS, and we are already doing it. It's just we need to motivate people more about it, and I guess we have to make people more aware about it, that yes, this can also lead to some kind of change.
Absolutely. And that's why I'm saying that there are some leadership which has happened in our country, and thus leadership in renewable energy has been seen by the world. There is leadership in this NBS as well, but someone else telling you how to do it rather than we document our stuff, so that we say that this is how it should be done. So for example, use of wetlands and constructive wetlands for doing sewage treatment, which will reduce your methane emission from waste sector, is going to be a game changer for us, because we are such a big population. We are using so much of fresh water, and all of our rivers are getting polluted. So we not only solve the problem, but we also mitigate climate change. So this is an area which needs a lot of focus. Thanks for highlighting.
Thank you so much.
Yeah, I am Rajan Varshne from NTPC. Actually, this nature-based solution, I want to just put a comment that the context and the perspective has to be changed. Like Niri had done a very good, is doing a good job in phytorate-based wastewater treatment. Actually, wastewater treatment, hardly we are treating our 30% wastewater, and that too is not getting adequately treated. So if we are going to treat our 100% wastewater, which is generated, lot of extra energy will be required. Electricity will be required, because present technologies are totally electricity based, and they are not achieving the best quality water also. Because a recent report also, which was instituted under NGT, I think you were also part of that. So only 2% water is getting adequately treated, the report said. So if we change the perspective and use these nature-based solutions to treat this wastewater, a lot of energy will be saved, and indirectly, a lot of pollution will be saved, or that CO2 emission during electricity generation will be reduced. Similarly, there are other things in which these things can be extrapolated, like whatever material stones are available, we can use those in construction. Why every individual in the remote village has to get the transported cement, which is highly CO2 emitting substance? And similarly, why everyone has to use the steel when we have bamboo and other things? So nature-based solution has to come to that perspective, I think. What is your view on this?
Yes. So almost 100% agree with you. Absolutely no doubt about it. The whole supply chain related thing is not yet addressed in our country and elsewhere as well, and that's where we have to bring focus. The second thing is, when we have done code writing, whether it's National Building Code or CPHU manual and others, they have been written almost like casted in stone. So when the tendering happens in any part of our country, it is written that way. So NBS as a concept is not integrated as yet. So the job of people like you and me has to be that how these codes become flexible regionally, so that some places local material can be used, and the tender actually gets floated like that. So even in Andamans, the tender of any civil structure is floated as per Delhi code, and then you have to import things from here and there. When I say import, I mean within country we import and export from one place to another. So a lot of these
DSR codes need
codes,
to be revised.
some of these codes needs to be changed, and some discussion should happen. So very rightly pointed out.
Thank you.
Yeah, codes have been designed. I agree that they are not designed to that extent, revised to that extent, which you are saying. But the codes have taken special care where the buildings, etc., are energy efficient. Energy efficient building code has been done by Bureau of Energy Efficiency, and CPWD in their manual code, building code, they have incorporated that, and it is mandatory to follow that now. No. And but then, as you say, that locally, if the stones are available, you need not go for bricks or something like that. Don't import it. I have seen in Rajasthan, they are building. The buildings are built by the local available stones, etc. And they are actually not importing those things. What you are saying, but that must be a local decision, not the general type of thing.
Codes have to incorporate those rates. Actually, this is the problem. While tendering, the estimate is prepared by those codes.
Of course. Okay. I think somewhere there is some deficiency which needs to be corrected with time.
We are doing, I just wanted to interject in the sense we are doing well in terms of bringing the code, National Building Code, Bureau of Energy Efficiency things which came up. Excellent documentation which got done. Delhi, they brought out a document which is called UT-PEG document for street design, which actually integrates almost every code of the country. But however, it is implemented only in one area, not rest of the other country. So what is needed is more and more such discussion where people become aware, which code to be used and how these codes can be further refined. I think that's where the challenge lies. Thank you.
Thank you. I think we must thank you, Dr. Rakesh, for joining us. And you said some medical reasons, etc. I hope you are okay, well now. And if you are facing some,
it was my spouse problem, not mine. So
okay,
thank you.
okay.
Thank you.
So we wish her well, and thank you very much for joining us and giving us a very detailed your own viewpoint. It was very useful to us to listen to you, and I think we will have more interaction in future. Thank you for joining us. Yeah. We would take up another we think that we missed that there was some tea break. Only break was there was no tea in this. So I thought this break we will miss and we'll have tea later. Let me invite Dr. Prakash D. Chaman.
We will add tea in that afterwards.
Yeah, you said break. So lunch was okay, but then Dr. Prakash will take up Indian coal gasification strategy, current status and way forward.
Yes.
Prakash, you listened to that discussion with your colleague earlier. So I hope you'll take care of that.
Definitely,
right?
sir.
Yeah.
Yes.
In coal gasification, you must tell us whether high ash coal, which we have, most of it.
Sure, I will cover.
How
those
far it
aspects
is,
also.
it is.
It is practically possible.
Yeah. Okay. And how much time we should give you?
20-25 minutes.
25 minutes. Is that okay? If you can maintain that time,
sure,
we will be grateful to you.
Yes.
Because everybody is feeling hungry for tea. Okay, Prakash,
Yes.
yes. Your time. You have some slides? Yes.
Yeah.
Okay.
I think it is audible as well as visible to all the audience online also. Thank you, madam, for giving me opportunity to share our experience related to mainly gasification as well as our views regarding the national policy. Yes, target is now, everybody is aware about the target. Important route is coal because we are talking about various economies, methanol economy, hydrogen economy, solar. But source is important, I think. We have, fortunately, coal as a potential source, but quantity is there, but certain important aspects are also missing. Most of the reserves are having high ash containing, except West Bengal ECL area. So we need to think in that direction, how to utilize those reserves. So we need to divide whatever resources are available, we need to divide into, because different ways are there through gasification also, for gasification route also. So all these resources we need to divide according to its suitability for particular gasifier, and then we need to make some policy. So since last 6-7 years, government is working very seriously. Before that also certain programs were there, but now it is in mission mode, and practically it is moving in right direction, we feel. So important, when we talk about gasification, 3 important aspects are there. Definitely technology, suitable technology rather. It should have wide acceptability for wide variety of feedstock. Because coal is a natural resource, so it is very difficult to get uniform quality of the particular coal, or particular, we can say, in narrow range, all the properties. So when we install any gasification facility, there will be certain constraints related to coal fuel properties. So it should be minimum for particular technology. Again, certain technical aspects are there linked with some specific technologies. We will not go into all those details, but a certain criteria is there for which particular technology we can call as a better or say best. So certain criteria is there. Once we select suitable technology, then another important aspect is operational philosophy. We will discuss definitely. And both these important aspects are linked with coal properties, or understanding rather, we will say, characteristics and its thorough understanding. So this triangle is very important. And if we see previous experience or failures or some unsuccessful stories, something was missing out of these three. That is the reason. At the end of this presentation, one can understand what was the missing. Understanding means definitely, always we talk about the proximate ultimate analysis, CV, ash content, all those important parameters only. But apart gasification point of view, around 12, 13 parameters are there. Out of those, most of the parameters are equally important to take decision related to suitable gasification technology, as well as how to operate it, operational philosophy. Why operational philosophy? Because for any chemical process where very standard chemicals are utilized as a raw material, so definitely we can get uniform specifications or characteristics of the feedstock. But in case of natural resource, it is not possible. So for chemical processes, we can go for standard operating procedure, but it is not true for mineral processing or phenomena like gasification. In this case, standard operating procedure linked with characteristics or understanding of characteristics is most important, rather more important than the technology. If technology have certain limitations, we can manage with the help of systematic understanding of the feedstock. That's why it is more important than the technology. So considering these aspects, we have done an extensive study in collaboration with Coal India, where we have completed gasification potential mapping. Mapping means we have prepared characterization matrix with all the listed characteristics. And on the basis of these characteristics, our understanding of all these characteristics, we have prepared what should be the utilization pattern, mine-wise utilization pattern, as well as what should be the suitable gasification technology for particular resource. And altogether, we have suggested gasification strategy for all these identified resources. And this particular report was submitted to Niti Aayog. And on the basis of these inputs, we have formulated a program wherein certain decisions has been taken by Niti Aayog regarding the what should be the commercial projects, how to move forward with indigenous technology, all those things. So this is one aspect related to understanding of feedstock. Now coming to the, just I'm giving brief about the available technologies. Basically, there are three technologies. I will not go into very basics of all these technologies. Just the difference is all these three technologies have certain pros and cons. First one, fixed bed. It is in practice in India also by JSPL in Odisha. It is in practice with high ash coal, but with certain limitations, and they have overcome all those limitations by taking certain steps. Steps means for this particular technology, we need to maintain ash content below 30%. Number one. Then certain particles, certain portion we can say during crushing fines will be generated. So we cannot utilize those fines. Certain part we need to utilize somewhere, or we can sell it in the open market. And another limitation is tar generation. So three limitations are there. They have accepted those limitations, and by addressing those limitations by another some way, they are using fixed bed technology to fulfill their requirements for DRI applications specifically, very successfully since last 5-6 years they are utilizing for DR application. They are comparing with conventional blast furnace, coke making and blast furnace business. And whenever both of these technologies they are parallelly utilizing, and they are gaining profit without any issue. And train flow technology, another successful. It is practiced worldwide, uh, in China mainly, and gasifier like Shell. It is widely acceptable, proven commercially. There is no any issue. Again, limitation is ash content for this particular gasifier. Ash content should be below 20%. Again, it is big problem for us. But by washing, blending, or blending with some another feedstock like pet coke, we can go for this technology also. So these two are no any if and buts for these two technologies. The only thing is ash content should be within acceptable limit. Third one is in view of indigenous or Indian resources, fluidized bed is quite acceptable. It has potential to utilize high ash coal without requiring any washing, blending, or any pre-processing. Only crushing to desired level is required, but it is not proven or tested technology. So this is the all about the available gasification technologies. So two programs are there to utilize commercially proven technologies by either washing or blending, utilization of Indian resource, high ash or low ash also. If it is low ash, no issue. With high ash, washing or blending will be required. Parallelly, development of indigenous technology under fluidized bed category. We have covered this part. So with these thoughts, government has formulated one program, option one, commercially proven technologies, under which certain installations are planned. Important one is Dankuni project, then TFL, Talcher Fertilizer Limited. For this particular project, shell gasifier is identified. It is in it will be installed in Talcher area in Odisha. So Dankuni, Talcher, these both are in we can say in already they have published tenders, identified shell gasifier as a suitable gasifier for this particular identified resources. For Dankuni project, ECL coal will be utilized, which is having ash content within acceptable range. So there is no any issue. For Talcher project, they have identified coal from Talcher area, high ash coal definitely. It will be blended with pet coke from Paradip refinery, and ash content will be bring down to acceptable range, and it will be utilized. Similarly, other few projects are also identified by Coal India. For successful storage, as we have discussed, using Lurgi gasifier, JSPL story. So this is all about commercially proven gasifiers, how to utilize. Then next, indigenous fluidized bed gasification technology development. All these four organizations, including Simper, BHL, Delhi Thermax joint venture, and EIL, these are working to develop indigenous technology. We have installed pilot scale facilities, and next target is development of demo scale. It's upscaling to demo scale. So till date, it is done successfully. So at demo scale level, both these commercially proven technologies and demo scale will be compared together, and considering all aspects, technical feasibility, economics, its provenness, facility, to what extent pre-processing and all those costs for commercially proven technologies will come in picture. Means thoroughly it will be compared, and then further decisions will be taken which one should be selected for to fulfill the government of India's target by 2030. So this is the complete program, government of India's complete program. So in parallel with this program, our institute is also having a very strategic program. So three important aspects are there. Mapping, already we have discussed. Then we have developed 1.5 TPD oxyblon fluidized bed gasification pilot plant. We have tested high ash coal from various coal fields. And presently we are in the process, already tender we have floated for 250 kg per day syngas to methanol pilot plant, consisting of complete downstream processing and conversion to methanol. So this was the earlier development. We have installed this particular facility in 2009. It is air-blown fluidized bed gasifier having a smaller capacity, 20 kg per hour. We have tested high ash coal mainly from various coal fields very successfully. Only coal as well as its blend with biomass also. And after conducting various experiments for several years, then we have upscaled this facility to 1.5 TPD oxyblown gasifier, because for value-added applications, it should be oxyblown to get concentrated syngas. This particular facility we have installed in 2020, and after that we have tested high ash coal having ash content up to 42%. We have tested, and we got syngas composition, CO hydrogen 25% and 30%. This is quite comparable with the commercially proven gasifiers, Lurgi gasifier. They are also getting similar syngas composition, but with comparatively lower ash containing coal. So this is with high ash containing coal. Carbon conversion, syngas yield, all these parameters are also quite attractive. So now we are trying to take this development for demo scale development.
You have 5 more minutes.
Sure. So these are the achievements. It is a clean gas. We have overcome all the operational issues like agglomeration, all those things. We have developed operational philosophy to handle high ash coal very successfully, and developed all the protocols related to what should be the startup procedure, steady state operation, shutdown, all those things required for commercial operation we have developed. We can skip this part. This is the syngas to methanol. So first part is existing gasification facility which we have developed, and at the downstream syngas water gas shift reaction, CO2 separation, and methanol. These three modules we are adding, so that it will be complete package right from coal gasification to methanol. For this, we are developing indigenous catalyst also. We are testing commercially available catalyst as well as catalyst developed at our institute. And this particular technology will be ready for upscaling. Starting the hydrogen generation, we have established water gas shift reaction where we can get through gasification and water gas shift reaction, we can get easily 70% hydrogen containing product gas, where just we get nitrogen around 23%, but it is because we are using PSA based oxygen generator. Otherwise, we can get more superior concentrated syngas, hydrogen gas, we can say. And further, with proven technologies, one can go for purest form of the hydrogen. This is methane related activity. So in summarized way, these are our observations related to indigenous development. When we compare all these three technologies, indigenization point of view, fluidized bed gasification technology indigenization is comparatively, we can say, easy, because entrant flow gasifier requires membrane wall lining, inside the gasifier, which is that particular development we do not have. In case of Lurgi gasifier, again, certain moving parts are there. Maintenance prone technology, that is particularly. So it is comparatively indigenization will be easy. Design development at pilot scale level, which already tested and designed for demo scale it is readily available. Consortium will be formed and it will be taken forward. Risk failure analysis of each and every module, we have completed this part also. Again, one important aspect which emerges always. So we have discussed SOP, standard operating procedure, cannot be utilized. So for variety of feedstocks, we need to go for utilization of the feedstock in the pilot scale facilities, as well as establishing the operational philosophy, feed specific operational philosophy, rather we can say, so that for its commercial exploitation, we can copy that particular operational philosophy and we can utilize in large scale gasifier also. Again, how to proceed? Just one suggestion. So if we go for a large capacity fluidized bed gasifier, risk factors are definitely more. So easy, we can say comparatively less risky and easy option is we can retrofit this particular new development with the existing facilities. We have very good facilities like GNFC in Bharuch, where already they are generating methanol, urea, and other products using syngas, but that particular syngas they are generating from natural gas. So just by putting this particular gasifier, we can supply them syngas generated through the gasification route, and downstream process, whatever processes are available there, infrastructure is available, that we can utilize. Once we get confidence with our technology, then we can replicate for other locations also. Then available infrastructure related to manpower, workshop, all those facilities we can utilize. So it is comparatively less risky option. Otherwise, another option is dedicated technology development park. So this is all about our view how we need to move forward for indigenous technology development suitable for high ash core. So again, in summarized way, just understanding of fuel is, yes, it is more important. High temperature membrane wall entry and flow technology, it is already selected for 2 projects. This is quite suitable for indigenous Indian coal resource specifically. Due to lack of time, we are not covering why it is suitable. Then indigenous technology development program, we have 2 options. Operational philosophy is important. And another aspect, apart from CO2 capture and utilization, polygeneration, nobody is talking, but it is one, we can say one of the important aspect to minimize the CO2 generation itself, or we can say in situ CO2 as well as byproduct utilization for value-added applications in the gasification complex itself, and then further utilization or sequestration, whatever CO2 remains unutilized. So this is all about our experience related to gasification. Thank you.
Thank you.
Thank you, Dr. Prakash.
Thank you. Thank you, sir.
We hope your research and experiment are very successful and we are able to gasify the high ash content core particularly. And unfortunately, the Government of India, you may be aware that resorted to that the notification says that you need not supply the washed core to the power stations. And that earlier limit of 30% ash content, 34% ash content core is now not there. This was...
It has not been taken back.
No.
That is for power projects.
Yeah.
But for gasification, because gasifiers will be installed at Myanmar only.
Yeah, that's okay. No, I'm just briefing you. And the Ministry of Coal and Coal India together, because Coal India was not able to supply the washed coal to the power projects. They somehow succeeded in notifying from the Ministry of Coal that there is no need for washed coal, and we are transporting unwashed coal to the power stations. It is very expensive.
Yes.
Can we take any questions on this coal gasification?
I have a question.
You have a question.
You said about the coal mapping for coal gasifier. So, is complete coal broadbanding has been done now, or it is only for gasification purpose?
For gasification, whatever parameters are there, around 12, 13 parameters.
Yeah.
So, targeting gasification application, we have characterized and prepared strategy not for other applications. Yes.
You talk about coal gasification. Have you also ventured about underground coal gasification?
Another group is there from our institute. Dr. Mende is also part of that particular area. So, at laboratory level only, not field level.
How deep you are going?
Pardon?
How deep you are going?
For underground? No, I think whatever developments are there, they have tried at laboratory scale only, not in field. There is no any exercise in India at least.
Navally also has been doing.
They are trying, but I don't know.
The problem that comes up is mapping of the coal seams. The coal seams keep varying. So when you start injecting and you inject thermal fire on that, will the fire pass through that coal seam or not? That becomes a big problem.
Yes.
I don't know further.
No, since after that, Navally has planned to do it. I remember that was earlier, first experiment,
right.
ONGC, and then Navally, is it successful?
No, there is no any successful story in India. At least. I think related to underground gasification.
Any more questions?
What do you do with the ash at your institute and all?
Sir, this ash can be utilized for backfilling of the mines as well as for construction purpose.
In the institute, you are doing this experiment, no? 1.5 ton. So their ash is lying as it is, or you are doing something?
We have departments for ash utilization related R&D. So brick making, so variety of products we can make, and we can say at large scale level, backfilling is the best option from construction. Otherwise, the aggregate making, all these the developed or proven technologies are already there. Jindal is having aggregate making plant. So from gasification ash, they are already they are producing aggregates which we can replace the gitti.
Yeah, we are also doing. NTPC is having so much ash. Yeah.
Already they have tested, they have constructed several buildings in their premises, but people hesitate to utilize that.
This interaction can take place during the tea time and convert into break only when So, thank you very much. And let me at the outset thank Dr. Malti Goyal. It is her efforts that we are here to do today. And she is so much of persuasive. And that is why she has been able to get people from such large distances. And Mr. Shahi, it's so difficult to get him and give his 5-10 minutes or whatever, but he also came.
35 minutes.
35 minutes he came. And it is because Dr. Malti, Mr. Shahi, and myself also, we are a part of a group called India Energy Forum. And but then this also equally good conference. And I'm also happy that so many people from engineering colleges and research students have come here and participated in this conference. And thank you, Dr. Malti. Thanks to
Thank
you.
you, sir.
Thank you.
For taking out your valuable.
Thanks to you.
Thank
Thank
you.
you.
Thank you, sir.
Thank you, Dr. Prakash.
Thank you.
Thank you.
And uprising about the developments in the power sector in the recent developments.
Power sector, if you have any questions, I can take up.
Just a minute.
Any question about the power sector, Indian power sector?
Sorry, sir.
Oh. Thank you for coming. Okay.